No, no, no. Sí, la frente te va a traer agua. O sea que te va a subir acá y te va a dejar el agua ahí.
¿Quién está pagando?
¿Ah?
¿Quién está pagando?
¿Pagando?
Dijiste que estaban pagando la comida.
¿Eh? No, pero o sea que ya terminaron, que iban camino para acá, eso me dijo.
Okay.
Pero yo tendría que estar aquí. Let's wait 2 more minutes. ¿Está bien?
Sí.
Igual, I'm going to say 2 words about Chiro because I just like all of you.
Say
Chiro.
And then I will say more than 2 words about Ricardo.
No, please, very
Mira,
short.
mira.
I was afraid of that. It's too...
It slips, huh?
Yeah, because it's like curved. It's curved. This part is curved.
Yeah, it slips.
So we need to put
Maybe you
something.
should...
No, we'll put something here.
Here, this one. This one should be square enough as a distance.
Yeah, but I
No,
mean,
that's not.
I will put it flat.
Yeah, that's
Yeah.
good.
There you go.
To engineers.
Maybe more central.
Otra cosa, ¿querés levalir o querés esto? Ese,
No,
como quieras.
aquí está. Recursive picture.
Y el hijo del hada está con mis hijos.
¿El hijo de quién?
¿Del hada?
Ah, sí.
Está con mis hijos.
Ya
Porque
tiene.
viajó Con el hijo,
¿Qué edad
9.
tiene? Ah, bueno, perfecto. Pero no está aquí.
No, pero está con el ahorita.
Ah, ok.
Okay. Let's say we just start.
Esperamos a la Loreta. ¿No?
¿Qué?
¿No quiere esperar a la Loreta?
Y no. Me pone de mal humor.
Ok. 15.
14.
No, 15 partes.
15.
Aparte.
All right. Thank you very much for coming back. I think the lunch was relatively quick, I suppose. We have a very full day today, and I want to keep on doing this double. There's an indirection in introductions here, a double indirection for those of you who are computer scientists. And I would like to introduce one person that will introduce another person, and the first person and the second person are very good friends of mine and extremely smart people. So I'm very, very proud to have them both here at the same time, actually. I think it's been the first time that you've both been in Chile, and it's really very nice to have them together. One of them is the director of the ISI Foundation, one of my favorite places intellectually to be at. And this is Ciro Catuto. So thank you, Ciro, for coming.
Thanks, Leo, for the indirection chain. So if there is one person who doesn't need introductions, in general, is Professor Ricardo Baeza-Yates, and in particular in this country and in this very wet computer. The computer is okay, I think.
But I think we should. Okay.
And in this country and in this city, I mean, really we don't need to introduce Ricardo. But since now he's busy cleaning up the computer, I have the opportunity to share with you for a couple of minutes a few highlights, just to reflect on how lucky and how proud we are to have him kick off this session. I mean, this morning we had a stellar speaker. This afternoon we start with another stellar speaker. So Professor Baeza-Yates is actually the CTO, the Chief Technology Officer on Intent, which is a semantic search company in California. He's also the director of the data science program of Northeastern University, the Silicon Valley, newly established Silicon Valley campus of Northeastern University in Silicon Valley. Until 2016, he was the vice president for research for Yahoo Labs, directing teams in Latin America, in the US, in Israel, and a world-class lab that you will certainly know in Barcelona in particular. He was until 2005, he was the director for the Center for Web Research here at the Computer Science Department of the University of Chile. He was the founder of the Web Science and Social Computing Research Group of the Università Pompeu Fabra in Barcelona, and is very well known for pioneering work in algorithms, data structures, information retrieval. If you study information retrieval, you study on Ricardo's book, which is called Modern Information Retrieval. The second edition won the Association for Information Science and Technology Award in 2012. And I can go on for a long time. Ricardo is an ACM Fellow, an IEEE Fellow, a recipient of the J.W. Graham Medal for Computation and Innovation, a corresponding member of the Chilean Academy of Sciences, a founding member of the Chilean Academy of Engineering. And since he is now back and the computer looks great, I will stop here. I will just ask you to give Ricardo a warm round of applause, and the floor is yours.
So thank you, Ciro. Never open a bottle of water near a computer. It was the same water. I hope it will survive. I don't know how much water is inside, but for the talk. So.
¿Está ya proyectando, Rodrigo? Rodrigo.
Sorry about that.
Sorry.
Okay, I will start with what I want to present today. So I think in the last maybe 1 year, we have heard news, some of them bad news. For example, in Arizona, an Uber car killed a woman. And then finally, and usually we worry about ethics after technology and should be before technology, people started to talk about explainable AI. So this is the topic of the presentation. So I will cover what is explainable AI, why do we need it, and here only we can have like a long discussion if this is possible or not. And I was a bit late because I wanted to put in my talk something that really recently happened with some controversial opinions. Then I will talk briefly about how do we try to solve the problem. I will give some examples. I will go to responsible AI, and then I will talk a bit more about the future, more philosophical, what will happen in the future. And many people is worried about this, other people is not worried. So they're like pessimist and optimist. So I will skip this, which is a very short introduction to machine learning and big data, depending on the audience. I will assume you know all this, so you don't need to hear this. So before going to the topic, I would like to introduce what is the problem complexity. And this slide is inspired by something that ISI organized in October in Torino. I was there and was in the Claudia Perlich invited talk. So let's say you have a complexity in the y-axis and size of data in the x-axis. And then let's say I try to do a classifier that will recognize me from other people. So it's just me. So just to, for example, for security reasons, I want my house only recognize me. And then it's not that difficult. So the complexity of the problem is not that difficult. I will have some unique features and basically will recognize my name. And this is a problem like low complexity. Now we can go to, let's say, a famous formula like Einstein formula, a linear formula. So basically the parameter there is the mass of the object. And this is big data in the sense that applies to any object. So after we know the formula, it's trivial. We can just apply it. And this is big data, but of course the complexity is very small because someone else did the hard part of solving the problem. Then we can have, let's say, Wall Street, so the stock market. That is very hard. It's almost like random. Otherwise, people will not be here. We'll be trying to gain the money there. But also, if that would be possible, the stock market would not exist because it would be trivial to kill it. And then we can have something more complicated. I don't know if you know this picture, one of my favorite pictures, the Garden of Delights, which has many animals in very strange shapes. So training a program to recognize every shape and then variations of these shapes will be not so easy. So that would be like big data and also large complexity will need to have a lot of training data. So this is the scope, and we need to remember what is the complexity of the problem every time we need to look at what a model is doing or not. So what is explainable AI? And here I will take, and many slides will have some source. So I will put the source of the slide everywhere. This comes from the DARPA program on the Department of Defense program of the US on explainable AI. It's called SHAI. Interesting, SHAI in Catalan is lamb, but I don't know if that's interesting, but if you search in Barcelona, you will find other things, like restaurants. And this is the definition. So can we answer these questions? Why did the AI system do that? Why it succeed? Why it failed? Can we correct an error? Can we trust it? Very important question if we are dealing with human lives. And here are some examples, famous examples like Watson, AlphaGo, and so on. So these are the goals of that program, and there are many people in the US funded by this program working on this. So today, the person that needs to receive the recommendation from, say, a machine learning model, they need to answer this question, and the person doesn't know how to answer these questions. And here is what we would like to have, like explainable model, and then do an explanation interface where the person can answer these questions. And here the person is happy, here the person is not. By the way, we talk about explainable AI, but this is like the joke. We use AI when we want to sell it, but we all know we are talking about machine learning, right? And of course, machine learning is a subset of AI, although some people don't know that. So the main first question is why we need such a system, why we need explainable AI. So here are some reasons. So the first one is verification of the system. So you need to have transparency. The second is for you, for the developer. You need to improve the system. Things like looking at the goals of the system. What are the trade-offs? Sometimes there are more than one goal. How sensible these systems are. What happens if you change something? And I will show examples that how sensible are neural nets to this. The third one is learning from the system, so learning causality, which is one of the main problems today. And then there are some that are very important because they are related to society. So the first one is you have to be compliant with law. For example, safety. One very important one, I will talk about that later, GDPR, the new privacy regulations in the EU. And then we have ethical issues. Maybe they're not lost yet, but they're important. Transparency again. Fairness. What about gender, race, and other problems that may happen, and you see in the news because of biased machine learning models. Here, let me give you an example of how sensible are these systems. This is a recent paper from Japanese researchers where they take very well-known image classification systems. Here there are 3 systems. And they change just 1 pixel. So you see this white pixel here. And then what was a sheep in the training data becomes a car to the system with very high probability, not low probability. And here you have another example. The horse becomes a frog, a deer becomes an airplane, and so on, just with 1 pixel change. So the question is, what the system is learning if you change 1 pixel and the tag changes, the label changes. And you can see that maybe some cases are, maybe you can have this confusion, but in general, cannot be confused. And I will get back to that question, what the system is learning. Well, why bias is important? Because it's very easy to learn bias from data. Here I have an example of data, not from the US, which will be the classical example. I want to put here from a different country. I found this about the UK. And this is from the 2011 census, but it's about 2014. This is only in England and Wales. This is the population split in different races. These are the arrests, these are the prosecutions, these are the convictions, and these are the people that go to jail. Of course, you can see here that if you are black, your probability of going to jail increases by like almost 4 times. So if you learn from this data, you will learn to be biased. Now, that is not always bad. I have another talk about using machine learning in justice, where there's some research that shows that even a biased system is better than people, better than judges. Why? Because they always take the same decisions. So they can be really more just in spite of being biased. So not always biased systems are bad, but you need to check what is the result. So why we need this? Let me give you another problem. And this is a paper on NIPS, 2017, so a bit more than 2 years. And this is a very interesting paper about learning maps using GANs. And this is from the paper I will read. The best is to quote the author. Says, the model learns to hide information about the source image into the images it generates in a nearly imperceptible high-frequency signal. This ensures that the generator can recover the original sample and thus satisfy the cyclic consistent requirement, while the generated image remains realistic. So in some sense, the system is learning to cheat, to like be successful, and at the same time do whatever the person wants the system to do. And that depends on the incentives. That depends also on the evaluation. So here is an example. Like here's the real photo. Here is the generated map by the model. If you see this building here that has all these dots, this dot disappears. But still the model can regenerate the image in the right way. But it's hiding these things because the system thinks they're not important to get what the person wants, the map. This one, this is the training map. So it's not doing a better map. It's trying to copy the map. And of course, if you do these systems, you want these systems to do it better than a human. So it shouldn't copy what we already have. It should be better. But it's very hard for the system to know what is better for us. So in this way, it's better just to copy. So this is another example of this system can be very sensitive to adversarial attack. In a very recent interview in Wired, Hinton did some controversial remarks, and this was picked up by Forbes. Maybe some people here read this recent article, trying to basically ask other experts if they think that he was right or not. So I would like to just read parts of this. It's like have like 8 pages of this. I try not to delete anything on the interview, but I just want to point a few things. So there are basically 4 things that he said, and I think I can spend some time reading this. So Hinton, and one of the fathers of deep learning in Google Brain, says, I'm an expert on trying to get the technology to work, not an expert on social policy. One place where I do have technical expertise that's relevant is whether regulators should insist that you can explain how your AI system works. I think that will be a complete disaster. Well, not too many people wanted to answer this question, but was one interesting answer from a person in Accenture, and I will only read part of the answer. Says, it sets up a false dichotomy between tech innovators versus regulators. And I agree with a lot on this answer. I will come back to this, because I think it's much better that we regulate ourselves rather than let lawyers regulate ourselves. It's a nightmare. I have suffered it. So we should be smarter and do the regulation in advance with the system. The second thing he said in this interview, and this is a very controversial one, says people can explain how they work for most of things they do. Do you agree? You can explain why you're here. When you hire somebody, the decision is based on all sorts of things you can quantify and then all sorts of gut feelings. People have no idea how they do that. And this reminds me of something I will talk later about emotions that are predictions, and I will relate to that. And if you ask them to explain their decision, you are forcing them to make up story. So basically, if I ask Chiro a question, Chiro will make up story. And she will make a very good one. Yeah? So one answer from a person in Australia say a lot of things, but this is the best answer so far. Is he making up story about this? Because basically this is an explanation of why we don't need an explanation. And I will get back to that. Because also sometimes you need to explain explanations, right? You need to transfer the language. We are good on writing technical terms, but maybe other people will not understand. So basically here people was not disagreed. Then the third thing he said was that neural nets have a similar problem. When you train a neural net, and I will shortcut, then you ask, why did it think that? Well, it's very hard to know from a neural net, and that's why people are working on this, on why it did that. And there are very interesting examples of basically retracing some mistake, and I will mention some of them to know why it happened. And here people partially agree that that is not trivial. However, some people say, of course, that comparing humans to neural nets is a false equivalence. I'm sure many people think about that. And I still believe that we are completely different. So the best chess game doesn't use the same ideas I used when I played chess. May beat me, but we think in a different way. So the question is how we can mimic that thinking. I think that's still an open problem. And at the end, this person says this is a red herring. And the other people that say, think, but let's go to the last question, the last controversial remark. In response to how do we trust systems, he says you should regulate them based on how they perform. And this is interesting because, I will repeat that again, we just need these systems to be better than us. They will never be perfect. And the only way to be better is to use us, so to be in control of the system. And here is mainly about bias, and there are several answers that is about bias and other things, like human in the loop. I will get back to that because I hate human in the loop. I don't want to be in the loop. I want to be in control. Okay? But this may be positive too. You can read the joke. So imagine that we don't need to talk to police any longer, and the cars can talk to each other, and problem is solved, I pay the fine, and so on. If my car cannot defend me, then I'm clearly wrong. The software, right? The software of the car. But of course, not always we need explainable AI. So when you have an automatic decision making, and this is what the acronym is being used in the European Union, not only for machine learning, so this could be any automatic decision. Like, for example, pressing a switch and getting a green or red light in customs, that's an automatic decision making. Someone is saying that you should be revised or not. And when we do not need this, well, many automatic systems don't have significant consequences. For example, here we have one example, web advertising. These are completely automatic. Maybe we have side effects, but not direct consequences. No one will die because of this. Postal code sorting, the same. Maybe a mistake, a letter goes to the wrong place, but most of the time no one will die from that. Or the other case is the problem is so well studied and you need to decide so fast that it's better to use a system. And I think the best example of this today is basically airport control. You have so many aircraft in some airports that maybe you can have a human to basically verify a decision, but not to take the decision because there's so much work, and this is so stressed people that emotions, lack of sleep, and other things gets on the way, like for judges, into taking the decision. So the problem, of course, is where is the line? Which systems can be or should be fully automated? So this is the explanation framework of the DARPA program, which I had already in the right-hand side. And then you have an explanation, and the user will make a decision based on the explanation. However, we have these systems where we don't have a human in the loop. And this is the ADM. And we have to remember that these recommendations, decisions, or actions are basically predictions. It's not the truth. And we'll get back to that. Because sometimes the predictions have very low support, but still are there. So the question is maybe sometimes you should say, I don't know. That's sometimes better than to give a prediction. And of course, why is this important? Because you need to be able to contest the system. To say, I disagree with the prediction, I need to change it, to whom I can talk. And I will get back to that because that's part of GDPR. Okay, so what are the challenges? There are many challenges because you need to learn the model, you need to explain the decision, you need to use the explanation. It's different if you have data analytics or you have, say, autonomic systems, and this is a good overview from the DARPA program about that. What could be an explanation example? And let's go to the explanation now. Well, this could be a cat, and this is the current explanation. This is a cat. Very important, this cat is just a translation from an image to a text. So it's translating this image to a label that says cat. But really the system doesn't have any idea of how complex is the cat. So this is like identifying my picture at the beginning I show. It's a translation from a picture of me to my name, but it still doesn't understand how complex I am. And this is very different from intelligence, and that's why I want to stress this. So this could be explanation. This is a cat, it has fur, whiskers, and claws, and has this feature, this main feature of a cat, this pointed ears. But explanations might be difficult. So what is this? Who can answer? It's a cat. Yeah. Some people that have cats take these, I don't know, silly pictures from below the glass table to, I don't know, see how the cat looks from below. I don't know. Maybe that needs an explanation, why that person took a picture. And then I want to say again, I mean, systems are afraid to say, I don't know. Maybe a typical system will say, this is a dog. It looks like a dog. But of course, it's not a dog. Basically, in this case, surely there was no picture like this in the training data. You just say, I don't know. So how many of you have trained a system where one class was, I don't know? OK. How many have trained a system where if the support, the probability of finding something is so low, you answer, I don't know? OK. You don't train systems, so you don't like I don't know. People don't like to say I don't know, but sometimes it's the best answer to do, especially with the teacher. So let's say the system guess is a cat. Why don't have some features? And I will get back to this. So very important, interpretability does not imply completeness. Completeness is very hard to achieve. It's impossible to have all possible training data about cats. And also remember, explanations may come from the data, the model, the process, many different places. And also you should contest all these places. So there are different ways to approach the problem. So you can make it more comprehensible, say adding descriptions. You can make it really interpretable, so it's a function, but it's very hard to come up with a function for the complex things. You may include reasoning. This is from the same paper of Doran et al., 2017. So here it says this is a factory, and here is an explanation of why this is a factory. So it has all the elements of a factory. Of course, you will find an example where something like this is not a factory. But most of the time, it is. So tackling the problem. So you have a lot of possible machine learning models here, the deep learning and random forest and so on. And here is like kind of approximation of the prediction accuracy, so the performance, and the explainability. For example, decision trees have very high explainability, but very low prediction accuracy. Random forests are better. Deep learning, very high performance, very low explainability. So what we want is to move this current line to the top and to the right. So how do you generate the explanation? So currently there are two main techniques. One is that you build a technique basically designed for the machine learning technique that you're using. For example, let's say deep learning, which is the most studied right now. Or you can try to do a technique that is independent of the model. So basically it works for any model. So let me give you examples of both cases. So this is like the previous example, but now you have actual points. So here you have, for example, and sorry that are the opposite. So performance is here, explainability is here. Here you have linear regression, decision trees, support vector machines, random forest, and at the end, neural nets. This is a model-specific approach. You move to the right. If you have a model-agnostic approach, you move to the top. And so I will show examples of both cases. So for example, two cases of explaining deep learning models. One, for example, by Bach et al. They basically do a decomposition of the feature space, and they do something called layer-wise relevant propagation. And that allows to explain the prediction. Other people, like Barnes et al., they do a sensitivity analysis using partial derivatives, trying to understand the backpropagation in the system itself. If you want to read more about this, there's a nice survey by Samek et al. That appeared 2017 about this. So here you need to understand how neural nets work, and you will come up with partial explanations that maybe are good enough to explain the system. Let me give you a model agnostic explanation. Then one of the most well-known is LIME, from local interpretable model agnostic explanation. And the idea is to use the system as a black box. So basically, put the system on a test and learn from the system. So basically like asking questions to you, and then finally you will say, okay, your hobby must be this because you answered all these questions correctly. And for example, here's an example of different inputs, and then the system learns that there's some boundary between the two classes here. So you explain a local boundary. So you don't explain everything, but you can explain this division here. So for example, this is this algorithm applied to this picture of a dog, well, the head of a dog with a person behind, playing a guitar. And then basically here's the explanation of the electric guitar. So it learns that this for the system was the guitar. Here explaining the acoustic guitar, learn that was more the outside of the guitar. And this is explaining the dog. So learn that can see a leg here and a face, because you have the dog with a person there. So it's a hard thing to explain. But not always worked. For example, this is a famous example of learning to distinguish wolves and dogs. And basically, the explanation is that the system learned to distinguish that wolves are with snow in the back, which is not the explanation you want, because a Eskimo dog will also be the same explanation. And also maybe a dog could be also with snow and so on. But of course, in most of the cases, that will work. So, you know, a lot of time is about majority ruling. Then we have the problem of evaluating these systems. And this is from a paper, a very interesting paper I saw also last October in Torino in the IEEE Data Science Conference. And here are 3 types of evaluations. So functionally grounded, human grounded, application grounded. And of course, every time it's more expensive because you need to involve first humans, and then you need to involve real tasks. So this will be an evaluation in production. So it's much harder to do. And here they look at basically that explanations is interpretability plus completeness. And interpretability will be things like GDPR or liability for automatic decision making. And completeness will be about explaining the wrong thing or why they're making decisions for the wrong reasons. And so explaining explanation is also a research problem. They look at 3 different types, like visual cues, the role of the individual units, and attention base. So these one are interpretable but not complete. These are complete but not interpretable. And these are interpretable but not complete. So you don't never get the free lunch. So the first one explains the process. The second explains the representation. And the third explains what you get. And of course, this is about completeness to the model. This is about completeness to other tasks. And this is about human evaluation. Is the result good or not? So they propose a taxonomy and best practices. And here you have the main result of the paper. It's available online, so you can go and read it. It's a very interesting paper. OK. So responsible AI. Let's go to GDPR. So how many people know GDPR here? How many people have suffered with GDPR? OK, some hands, OK. Okay. So this is the actual Article 22 that talks about automatic individual decision making. And this is the copy and paste of the article. So there's nothing changed. I put here in red only this one that is in the last line, which I think is a very important one. You need to be able to contest the decision. If you disagree, you have to do it. In the US, this already happened once, although there's no GDPR there. There was a person complaining about the bank system decision, and basically the reasons were unconstitutional, and that person had to go to the Supreme Court to win the case. This happened about 2 years ago in Atlanta. So if you read this, it's a bit ambiguous. Okay, yes, it was written by lawyers. I don't know if there are lawyers here, sorry. But let me put this in more simple words. So to know if your system fails under this article, so basically to know if you need to worry about GDPR or not, even if you are not in Europe, you may need to worry because you may have European users. So if you're using machine learning, you at least need interpretability. You will need this. And then you will need to introduce simple ways for the users to request human intervention or challenge a decision. Again, if you're using machine learning, you may need to explain. And this also implies that you have to do regular checks to make sure that your systems are working as you designed it for. You know, you change a bug, you solve a problem. Maybe you need to do it all again because the system is not working properly now. So if this is a continuous thing, it's not something you need to do at the design stage and then you forget for this forever. A related topic I want to mention here about this complexity of problems and explainability is related to data science. So let's say we have this graph where data is on the y-axis and the companies, the institutions having this data are in the y-axis. So this is a long tail of data. This is almost all the institutions in the world that will never have big data. Big data is only for big companies. If you are a bakery in a corner, you will never have big data. And depending on the definition of big data, that will never happen. So why is it important? Because there's a lot of small data around there. Most of the data today is small data. And we are not worrying too much about small data. I think that's important. We need to worry about small data. Small data is the problem. It's much harder. And here are some reasons why small data is important. And even it's a book about small data that appeared a couple of years ago. And one very important thing, small data is easier to explain, right? So one possibility is not to change the system, to change the data. Now, if you want to read more about this, I wrote a position article in KD Nuggets in October, and this was the most read article that month. So at least resonated to some people. But talking about this book, this book says that most innovation are triggered by small data. So I guess to innovate, you need to be bored, and then small data. You need to be bored. There's some people, you need to think about it. So if you're always busy looking at your phone, you will never be bored. And you can look at this table in the article in KD Nuggets, but this is the comparison between small data and big data. And big data is easy. One solution for big data is to put more data. So many problems, just put more data and the classifier will work. But sometimes you don't have more data. This is an example I'm working with a former PhD student and a new PhD student about basically detecting people with dyslexia. And for example, with 4,000 people, you can get 81% accuracy. But in English, with 1,500 people, we can get 90% accuracy. So here, you change the language, and you can do better. So this is the important part of the example. Sometimes if you change the problem, you can do also better. Why? Because Spanish is phonetic, so it's much harder to detect the mistakes. English is not phonetic, so a lot of mistakes. These people with dyslexia do a lot of these mistakes. And of course, for example, like in many other cases, the cost of false negatives, not detecting a person with dyslexia, is much more costly than, for example, false positives. Let's say sending a person that doesn't have dyslexia to a specialist, that after seeing the specialist will be very happy because that person will not, doesn't have dyslexia. Okay, so let's go to some practical aspects. So legal and ethical issues. And I will not read this. There are too many factors involved. There are cultural issues. There are legal issues. They are all different in every country. So let's say you have ethical algorithms. Maybe they need to prove the explanation, because if it's true that we can make an app story, then maybe the story is false. How we can prove it? For example, if you do a zero knowledge proof, how you can prove to a non-computer science person that that proof is true? I would guess they will never believe you. You only believe because you have understood the zero knowledge proof. So exactly 2 years ago, the ACM US policy group did a statement on algorithm transparency and accountability and said that all algorithms should fulfill these 7 properties. One of them is explanation. And I will not get into details here. But for example, they don't have to be perfect, just better than humans. How many algorithms have these properties? And none. Even one of them will be hard to find. For example, this is very important related to GDPR and also related to the new copyright directive of the European Union, if you know what I'm talking about. So it's related to the right to be forgotten before, and now to the right to detect bots and so on. So what are the bad human practices that maybe we can stop to have better explanations? For example, learn from the past without remembering the context. Learn from bias. Not checking for proxies or correlated information. Reusing code in different contexts. Although there seems to be history of computer science where we design one system for one goal, like Unix, and then we use it for everything. Tendency from companies to resist review, especially, for example, companies in the US that are doing systems for justice. Conflict of interest. Failing to measure the impact of the system. Personalization to the very low level instead of using personas, so harming people. There's a trade-off with privacy here. Or basically using inaccurate data or just data that you have. But maybe some bad practices are good. I don't know if you saw this joke recently in your social networks, but if military robots use history from the really far past, we are fine. Right. However, there are hard learning problems. I will get back to this image. How do you know this is a cat? You know that it's a cat because you have an abstraction of a cat in your mind. You are able to forget. And this is very important. To learn, you need to forget. You need to abstract. Not sure if neural nets can forget everything. And I like to recall this one of the amazing stories by Borges, Funes de Memorius, that was a person that couldn't forget. So you had the bad idea to say, how was your morning? You had to wait a morning to hear the story, because he will tell the whole morning. So, but he had no friends at the end. Yeah? But this is the problem. We forget a lot of things. Our brain can forget. But also very important, you cannot learn what is not in the data. And some people seem to believe that training data is magic, that everything is there. I think will be much more important in, for example, doing research in how to get better training data than rather trying to improve your machine learning technique. Because better data, you will get better output. Like this example, you can read it. So in this case, the person forgot the ethics code for the robots, like the 3 laws of robot of Asimov, and then the robot is very dangerous now. So some recommendations. So design for people first. Respect the limitations of our systems. Learning from the past doesn't mean to reproduce it. It means to learn, which is very different. We need to enforce code of ethics. Now we are seeing more of this, but it's still not 100%. We need to improve explainability, even if Hinton disagrees. More evaluation and cross-discipline validation. That's very important. We need to work with the people that need these systems. Research best practices with humans in control and machines in the loop. So please don't use human in the loop. We designed the system, we developed the system, we deployed the system. A human at the end verifying the decision is not a human in the loop, it's just a user. It's not us. And as other people say, we need to study more intelligence and consciousness, not only artificial intelligence. We need to close the gap between, let's say, neuroscience and AI. In the future, we may upgrade some jobs like teaching or children care. These jobs will be very important if we need to teach robots. We need to learn much more than today. We need to improve education if you want to keep up with this evolution. Why? Because this is what I'm really worried about. You can read the joke. I'm not worried about robots. I'm worried about people. In every election, I get more worried. And I don't know what to do. And I will cite the last book of Harari, these 21 lessons for the 21st century. He says, and I will get back to that in the next slide, the real problem with robots is not their AI intelligence, but the natural stupidity and cruelty of their human masters. We are the ones that don't do the right thing. Why? Because if this keeps going on, we will get to another joke. So the robot goes to a system, says, prove you are not the human. The robot says there are no more humans. The system says correct, and they both laugh. And not because the robots kill everybody, it's because we killed ourselves. Before we had the atomic bomb on the head, now we have, I guess, robots. So what is the future? It's really dark. I'm an optimist, but after reading this book by Harari, it's hard to be an optimist, but still I'm an optimist, because he said that free will is an illusion. So how many people here read this book? 1, good. 3, good. I don't agree with everything he says, but I think it's very important that we read it. He says something that really worries me, that humans can be hacked. I believe, and all of you believe, that you cannot be hacked, right? Even though every election shows that a lot of people are hacked. So the question is, maybe we are complex and then some easy parts can be hacked, like politics. So some people can be hacked in politics, but for example, for people that love culture or football, it's very hard to change your team, right? That's very hard to hack. It's like hard-coded in your brain by your dad there, right? So there are some parts that maybe are not hackable, like your spouse, I hope. But maybe politics is easy. But this relates to some very interesting book about emotions are prediction from Lisa Feldman Barrett less than 2 years ago, that says that the brain works like a machine learning system, that basically every emotion is a prediction that you learn when you're a kid. But the important part of this is that you can retrain yourself. So next time, if you really don't like one of your emotions, you can train it. That means, for example, you are about to get angry, and you said, no, this is just a prediction. The prediction is wrong. I will stay put. Your face will look strange, but no, I will not get angry. I have done this, and it works. I'm angry less time now. Loss of jobs. Maybe we can leverage AI. Maybe we can work for robots. Why not? On the other hand, I don't have any problem if you give me all my time back, and I will write and do everything that I like. So I do not worry about the job. I will worry about the salary. So we need a universal salary too. But we can do more literature and art. Imagine that all the people can finally pursue their artistic will. Loss of skills. This is very important. So how many people here cannot find the place without their phone? One. Few. Well, train yourself. Go to some places without your phone. Well, you have it just in case, but don't use it. It's true. When they're better than humans, you should use it. But we need to keep these skills we have from evolution that are very important, because when you have no phones, no energy, no nothing, maybe we'll need to be able to have these skills again. One important distinction he does between, let's say, automated systems and people is that they are in a network. And here he's completely right. So imagine all robots communicating. They are a network. The good thing is that the systems are so silly that they have to communicate in human languages. For example, Siri has to talk to Alexa in natural language. They could communicate without us seeing anything encrypted, but now we still can see how they talk, because some they don't want to talk to each other. But imagine if they want to talk to each other. We will never hear them. And then, if that happens, the authority goes to the algorithms and the owners of our data. Luckily, all the data now is in different silos, so no one owns all the data, and I hope that never happens. But this may be a future. And then that will imply more inequality, and finally, something very important, no sense of purpose. But this is not related to also the dark future. He says that most animals know why they're on Earth. They know what to do all their life. We seem to not know exactly where we're going. And I understand what he's saying. That's why I don't understand, because we don't know where we're going, right? And then, if you have no sense of purpose, you have irrelevance, which is very sad in some sense. Well, here I try to basically disagree with him. I'm still working on this. I hope to disagree more. So the epilogue. Maybe no privacy. Maybe we are willing to give our data if we get something like 20 more years of life. But if we have algorithms that fulfill these 7 properties, this is a nightmare for me, because this may mean software insurance. This is the easiest solution to wrong software. Okay, let's pay something. But then that means that will become like health in the US. Things will be more expensive and not necessarily better. Ethics for robots. Augmented humanity. If you read other people that believe we will become gods. I'm quoting Harari again. Either democracy will successfully reinvent itself in a radically new form of humanity, or humanity will live in digital dictatorships. They said, sorry, there's a mistake there. Why I did that. If I don't fix it now, I will never fix it. I know my mistakes. Why so slow? Okay. I will never fix it again. I learned that. Still, I believe technological change is good. However, if you see the election in Philippines in 2017, I guess I should put Brazil now, 2018. Or if you have read about social score in China. So how many people watched the nosedive episode of Black Mirrors? Okay, that was supposed to happen many years in the future. It's happening now. However, I just saw a documentary. You can find it by box, not the Spanish box, a different box. I found it. You can find it in YouTube, where it seems that thanks to this credit score, this social score, people is behaving better. So people is having nicer neighbors, and people is behaving nicer with other people because of this social score. So maybe it's a good thing, who knows? But I'm worried that we are evolving towards Solaria. How many people read this book by Asimov? I'm a science fiction fan. So in Solaria, every person has a few thousand squares of land, 1,000 square miles of land, and then they live alone. Robots have solved everything, including reproduction, which is very boring. But then the book comes from a different line when there's a first time in many years there's a crime. But in this case, I want to to say that losing this social aspect and become like this world will be a pity. So basically, we're disconnected from each other. However, this is my wish for this new year. If you saw the movie Arrival, I want them to come as soon as possible. Maybe that's the only solution to become all together, and China talks to Russia and talks to Trump and so on, even if they cannot talk. So, questions? Dennis has a question.
Thanks for the talk, Ricardo. Very enlightening, very, very interesting topic. One thing you did not mention, and I would like to have your opinion about it, is sometimes there are a lot of disinformation in the news regarding AI. And one example is related to one example you gave. You gave this cycle gun used to transfer from one type of map to this more like map projection, and then go back. And what the scientists, the researchers discovered is that actually the cycle gun was trying to hide some information, so to make easier the process. But the way that a news outlet reported this was a clever AI is hiding information from its creators.
Yes.
So that's completely like a misleading way of talking about AI. So since we are more technical, and thanks to talks like yours, we can understand the real dangers of AI. But when the news present the AI in this way, they just get it completely wrong. So what's your position on this, or your comments?
That's a very hard problem, because I think it has to do with natural intelligence, not with artificial intelligence. So it's much harder. So yeah, I think there's a problem in media, a deep problem now in media, that the only way to sell is to basically, if you have, let's say, don't count fake news, but to sell things in a way that people will be enticed to read. And then you get these misleading titles, you get these misleading comments. In many cases, the people don't understand what they are reading, because, for example, I read that paper, and I'm sure that journalists will not understand most of it. So I don't know what is the solution. The solution may be to forbid journalists to read scientific papers. I don't know if you can do that, but this would be a possible solution. Like you have two versions. So if the IP comes from a media site, you give like a one-page summary in their language. And if you come from a university, you can download the real paper. They will never notice the difference. So something like that. It sounds like a joke, but I think it's more serious than I'm saying. And that, I think, is related to the same problem of natural intelligence, right? I mentioned. It's about education. So how can we educate people to question more, to read more, to write differently? And that's it's not a technical problem, that's a social problem. I don't have an answer, so I really don't know. And I'm not afraid to say don't know.
Okay, thank you.
So there was a question on that side? Yeah.
So I have a question that's related to the previous one, and since most of the audience here seems to be related to computer science, how would you put in this picture when you say, well, natural language or natural intelligence versus artificial intelligence seems to me much like an old question versus I mean, it speaks about predictability versus explainability, right? So is there a way, from your experience and perspective, to try to approach this big issue that that the development of AI is trying to assess, which is trying to understand the system in the first place and then to predict it, maybe perhaps, or, I mean, how can we go along that way?
So, not sure if I'm answered that question, but I was thinking on Dennis' question, so it's related. And maybe we can do systems, for example, we can do systems that take a paper and write a nice explanation about the paper, like a one-page explanation for any person. And we have a good training example. So we do have good media articles about papers. So we can say, okay, this is a bad example, this is a good example. Maybe we can come up with a system that basically, maybe it's invented a research topic. Maybe someone is already working about this, about writing summaries that anyone can read from a paper. So this would be a possibility, because then at least you will have one. For example, typically what is happening today in the news, that someone says something about a company, and then the next day you have explanation of 3-4 companies about why the article was not true, or why the article was misleading. It would be much better if that is already there before that article. So basically, every time you do something, you say, okay, this is the explanation. And we have plenty of explanation for people to read and not to wait for, say, a New York Times article to know. In fact, this article that Dennis was mentioning just came out like 1-2 weeks ago, and the paper is 2017. So someone said, oh, read this paper, this is a good paper for an article. So this is the other problem. So it's not even timely.
Yeah, just to here.
Yeah, okay.
Yeah, just to add on the same thing. Actually, I was discussing about this with my colleagues at USC, that it's actually a big problem in science in general, that we do not approach general population. And actually that affects in a lot of levels, including, for example, in funding. If we don't get more funding for science, for example, it's because people don't see science as something important, right? Mm-hmm. But if we are able to actually train PhD students and new scientists about the importance of communicating their research to general audience, that wouldn't be such a big problem right now.
Yeah, I agree, but there's so many cultural things that are very hard to change, right? Thank you.
So thank you, Rick and Chiro, for moderating. So we will have a very short break now. So we'll go and stretch your legs. If you want to go grab a coffee at the Starbucks, that's fine, but be back as soon as possible. We'll give you like 10 to 15 minutes to come back. We're a little bit late, and I don't like being late. It's like, I don't know, obsessive compulsiveness. I'm not sure. Anyway, so go stretch your legs, please.
Hey!
So guys, maybe we can start again. It's a long day. We have a lot of material to cover. So one thing that you might maybe be happy about is that one of the papers have been canceled in this session. So we're going to leave a little bit earlier in that sense. So it's not something that I'm very happy about, but whatever. So the coffee will be 20 minutes earlier, which is awesome. And yeah, so I'm going to leave you with Sam of Northeastern, Sam Scarpino. We're very happy to have him, and he'll be chairing the next section. Thank you.
Yes, so thanks very much. And our first speaker, I actually don't know who the first speaker is because there are 4 names on the paper. And I haven't met the speaker before, so I will let them introduce themselves with apologies. And
I'm going to wait.
Yeah, so it would be a nice idea for the speakers to actually introduce yourselves to Sam, so poor guy knows who you are. So.
Well, I will introduce myself.
Yeah.
Meanwhile, yes, my name is Miguel Guevara. I'm from Valparaiso. I work at the Universidad de Playa Ancha here in Chile, and this is a joint work with my colleagues Dominic Hartmann, Luciano Di Giampietri, and Esteban Fernandez from the USP in Brazil. Yes. Basically, we want to present our work in mapping the scientific output of Brazilian institutions. What about maps? We've, like a society, have been creating these maps of science at the beginning, trees of knowledge or something like that from ancient times. And with the appearance of the first journals, the French journal and the British journal, we can gather some information from that, from those publications. And with those information in the modern times, we can create networks based on that information. For example, networks based on citations, on co-citations, on international collaboration, on co-authorship, and so on. We are particularly interested in this type of networks. These are networks where you have the nodes, and the nodes are areas of science or fields of science, and the edges are some measure of similarity. For example, the number of citations that you can find between both areas of science. These are the so-called maps of science. And the main approaches are related to citation approaches. You have here to the left the UCSD map. That is a work of Cathy Bonner and colleagues, and it's based on bibliographic coupling. And the global map of science at the right is a work of Ismael Raffles and colleagues. Those are the main approaches that mainly are based on citations. But this is like the traditional approach that is mainly how to classify science. It's a bit like this knowledge tree. That's the traditional approach, how to classify science or how does science how to classify. Yes? But, and this approach is based mainly on three methods that you can find there. It's co-citation, is direct citation, and is bibliographic coupling. Those are the traditional methods to create this type of maps. But what we want to propose is a map, and a map is useful to find where am I in the map and where can I go in that map, not just to classify science. So our approach is based on career paths, and in our approach we are taking in account the production of papers based on the capabilities of the scholars. Yeah? And why we want to do this? Mainly because you have some fields of science that you have developed because you are publishing in those fields of science, and you have some budget that you want to spend in some fields that you want to develop. But you cannot put money on all those fields that you want to develop, so you have to make some sorted list of which are the areas of science that you want to prioritize. This is our proposal, and we published this a few years ago in a joint work. It's called the research space. And the research space is mainly based on production capabilities of the scholars. So we want to go from where are publishing the scholars in which areas of science, and based on that information, we want to create the network of similarities between areas of science. But to do this, we had a problem because we need to find some data set that is disambiguated to the level of individuals. And you know that the Web of Science and Scopus are not that good in disambiguating data, at least a few years ago. So we crawled Google Scholar, and Google Scholar is interesting because you have to clean the publications that you have in your list of publications. It's a sort of crowdsourcer database. And we can follow the links to your co-authors, and we can follow the links to their publications, and then we can get an interesting connected component of Google Scholar. And that's what we did. After that, we need some classification of science because we want to map your publications with the areas of science. And to do this, we used SIMAGO classification, that is mainly Scopus. And we used the UCSD classification, that is the classification proposed for Cathy Bonner in the map of science called UCSD for University of California in San Diego. And with these two classifications, then we can make our match. So we go from the publications in Google Scholar, and we use the name of that publication, the name of the journal, and we then go to look that name in the classification of journals, in this case in Scopus. So we can map a line from the scholar to the area of science in which that scholar is publishing. And that's quite interesting. So in that time, we used a data based on 12 million of publications, more than 300,000 authors, and more than 7,000 institutions. And we used both classifications, SCImago and UCSD classification. In SCImago, you have roughly 300 areas of science, and in UCSD, you have like 500 areas of science. By doing this, we are able to find first the diversity of scientific production. For example, in the top of these images, you have Ed Boyden, and he's mainly a neuroscientist. You have Laszlo, and he publishes mainly in journals that are multidisciplinary and physics and astronomy. And you also have Ricardo, that is publishing mainly in computer science, mathematics, and so on, and also in some papers in social sciences. With this diversity information, we can build the research space. For the research space, we use first a measure of authorship that we call X. With that measure of authorship, we can find the intensity of publication of a scholar in some area of science. And with that intensity, we find our first network. That is a matrix that in the rows, it shows the scholars, and in the columns, it shows the areas of science. But we want to use this matrix to create another matrix that is our network of similarities between areas of science. And that's our map of science that we can use. And here you have a graphical representation of this research space. As I said, this was a joint work with my colleagues 2 years ago. With this map, for this proposal, what we are going to do is to map the scientific output production of Brazilian institutions. To understand this, first I want to show you how we process the data that we got from the Brazilian database. To do this, I'm going to show you an example. This is from our previous, another paper, and I'm going to use that because I think that is quite explanatory. Here we have the production of countries in number of papers in some areas of science. Okay, so here you can see. Okay, here you can see. Well, you cannot see that much, but you mainly can learn from here that the United States is publishing a lot in medicine. But you don't know anything, any other information from the other countries, right? So we want to use proportions. We want to see how important is each area of science inside that country. So here we have a bit more of information. For example, we can see that Argentina is publishing from its local production, is publishing mainly in agricultural and biological sciences. So if we use share or proportions, we can learn more from the data. But this is not enough because that's a relative measure inside each country. And we want to compare each production of each country with the rest of the countries. To do this, we use a measure that is very used in econometrics that is called revealed comparative advantages, the RCAs. So to compute the RCAs, you take the share of, as in the equation there, you take the share of that country in that particular field, and you divide it over the total production of the world in that category. So here we can find that, for example, Argentina has revealed comparative advantages in agriculture and biological science, but it has also RCAs on veterinary, for example, because its local production in percentage, in proportion, is bigger than the production in the world in proportion. Yeah? or is bigger than the expected in the world in that particular area of science. This is very well used in economic networks. And here we are using that for this type of production. So with that example in mind, we took the scientific output of Brazilian scholars. The database from that country you can find in LATE's website. That is the official site of Brazilian agencies of funding research. So you can get all the information of all scholars that are publishing with funding from Brazil in that database. Yeah? So we got information from that you can see there. It's number of authors. We have more than 169,000 authors. We have more than 2,000 institutions. We have more than 800,000 publications and more than 10,000 authors in an interval that goes from 1943 to 2016. Yeah? And we can use that information in different levels of aggregations from individuals, institutions, and regions. We're going to use the information for this proposal only at the level of institutions. That is what we want to evaluate. Okay? To make the evaluation over the map, we define states. These states can be inactive, that you are producing nothing in that field, or active. And if you have some nodes that are active, we can define some states for active nodes. These states, as you can see there, are based on RCAs. If you have an RCA that is lower than 0.5, we say that that is a node that is nascent. And if in your RCA is between 0.5 and 1, we say that that state of that node is intermediate. And if you have more than 1, we say that that node is already developed. Okay? And defining those states, then we can overlay the information of Brazil or institutions on those on our map of science. Yeah? And here you can see an example on how those institutions are evolving across the time. It's just a random example. Okay? And we can see the nodes that you already have developed, which are intermediate and which are nodes that are nascent, and which are the nodes that you do not have developed. Now, how can we recommend the areas where you should go based on that information? We define this measure that we call the density. And if we take a node that is inactive, for example, biochemistry, and surrounding that node, you have other nodes, like, for example, biology or chemistry, and you have already developed those nodes, then we can presume that in the next time step, you are going to develop that node, mainly because you are surrounded, that node is surrounded by other nodes that are already developed. And taking this in account, we see that the next time step, that node is going to be activated. The emergence is highly probable. But if you have another node that is surrounded only for one node that is already developed, the emergence is probable. But if you have one node that is surrounded for none other node that is already developed, well, then we can think that that emergence of that node is not that probable, right? If we compute this, for example, in the first row, you can see that we can suggest a density of 1 because you have 4 links connected to other 4 links that are already developed, and then you can compute that probability is 1, and so on. The last one has probability 0. By doing this, we make our recommendation. We make a list, a sorted list based on density, and in the list you have an inactive field A, and in the other time step, that field is going to be developed, so you can plot and you can advance in the ROC curve. You can advance in the y-axis because that's a true positive. But if you go with another positive, so you go in the rate of the two positives. But if you don't develop that node that is in 4 position, so you advance in the x-axis, that is the false positive rate, right? And so on. Then we have our ROC curve, and you can compute the area under the curve. For example, if you have an area under the curve is 0.5, we can say that it's much better than random at least. Okay? And here we have some examples of ROC curves. And to make that evaluation, we used these transitions. We are evaluating from inactive to active, and from nascent to developed, and from intermediate to developed. Here we use data only in the interval from 2010 to 2016. And we aggregated that data each 3 years, and we used 189 most productive Brazilian institutions. If we use our method that I showed before, we can find that in the first transition, we get good results. It's roughly in average 0.75. And in the second transition and in the third transition, mainly we do not have that good results. So in conclusions, we use the research space to map scientific output. The measure of density is a better predictor for producers with less developed nodes. And transitions from inactive to active gets better results, as you can see. In our ongoing work, we extend the analysis to meson region level in Brazil. That categorization is quite interesting. And by doing that, we can find a correlation between the activation of new fields of science and the presence of new industries in the regions of Brazil. That's what we are going to make in the next step. Thank you.
All right, so we have time for a couple of questions. So I have one question. Sorry, I just unplugged your computer. Sorry. For Google Scholar, I'm aware of an issue they have with preprints and then published articles sometimes not being resolved appropriately. What kind of bias do you think that might introduce?
We are deleting that bias in the sense that we are matching the text of that publication with the text in the classification. So if you have, for example, a PPT or something that is not already published in some journal, then that publication is going to be deleted from our data set. Yes, because we are matching only the publications that already appeared in some journal indexed by UCSD or by Scopus. Yeah.
Any other questions? I'll ask one more then. So I get thinking then about biases by field in terms of publishing only in preprints, like maybe physics, for example. Do you notice anything like that?
Not yet, because we, as we show, we are using these RCAs, and so you can find some advantages between countries and between areas of science. So yes, we have the distribution of the publications for each area of science, and yes, always medicine is the first one, but that's also common in other databases like in Scopus or Web of Science. Yeah.
Great. All right, if there are no other questions, let's thank the speaker again.
Thank you.
And as a reminder to the fourth speaker, you'll be going third, so after this next speaker. Okay, great.
Hello? So I'm Albert Macau from National Institute for Space Research and also from Federal University of São Paulo, Unifesp. First of all, I'd like to thank you, Leo and Bruno, for put forward this conference, doing some nice work. Thank you so much. And my institute, INPE, He's responsible, he's located in São José dos Campos, nearby São Paulo, and he is responsible for the Brazilian space program. It means we launch satellites. But today we are going to talk about recurrence measurement of conditional dependence. First of all, let me, this is my co-workers, Antônio Mário, my former postdoc, Dr. Norbert Marvan, and Dr. Jürgen Kurf. First of all, let me ask you, you know who is this guy? Nobody knows? Well, this is the famous Raffaello Sanzio. He lived in Florence for 4 years, and he did so many nice artist work. And you know he passed away in 1520, so in 2 years you are going to celebrate his 100 years of death. And he did so nice work. He's one of the 3rd masters in art in Italy. And I'm going to ask you talk about this Athens School. This is a very nice painting that is located in Vaticano, in Santa della Signature. It was in the former library in Vaticano that was built by Julius II, the Pope Julius II. And if you take a look at this amazing painting, we are going to see very nice features. Like, for example, in the center of the painting, we see Plato and Aristoteles. Plato pointing to the up, and while Aristoteles pointing to the down. It means that he is mentioned the philosophy, because this painting is out of philosophy. And he is about the theoretical philosophy, Plato, while Aristotle is about natural philosophy, it means science. And you can see they are talking to each other. And all over this painting, you can see other people talking. For example, Alexander the Great talk with Socrates. We can also see Pythagoras demonstrating a theorem, while Euclides is talking about something, showing about this theorem to the people. And other famous guys, for example, Michelangelo, and other people are talking about. So the main point is that we have a lot of conversation here. And we want to know who is influential to each other. For example, what those guys are talking to each other. They have influence in what is Pythagoras doing here, and other things like that. So we're here concerned about flow of interactions. How can we find out flow of interactions in a scenario like that? So, for example, imagine that we have our brain, and you're going to do some measures using, for example, EEG, for example. So we have several points, and out of these several points, we are going to record the data set, and for all these points, and what we wanted to do is to find out who is influenciated each other. It means we want to do the interaction network to find out the approach considers each part of measure. So out of a pair of measures, we are going to come out with the network that is responsible for interaction between this part of the brain, for example. There are so many applications related to that. And what we are going to do is to show to you one approach that we came out about that. Our approach is based on the concept of recurrence. The concept of recurrence came out of this theorem about Poincaré. What Poincaré tells to us and prove mathematically is that if you have a system, and this system, it means that is system over the time, the states came close to each other over the time. It means that the states, they recur over the time, a lot of times for all the time. So it means, for example, if you consider the Lorentz system, here we have the 3D projections. If you see what's going on, we are able to see that trajectories, nearby trajectories, they deviate from each other, but from time to time they came close to each other, which means that they recur, they come close to each other over the time. So, but this theorem does not tell to us how long it takes for a trajectory to recur. And in 1987, Ekman came up with a brilliant idea of how to take out this recurrence concept in a mathematical framework. It means that if you have a trajectory, actually this is a trajectory in state space, and we have the time, And we measure for each point of the trajectory when they come close to each other for inside an epsilon distance, and record it in a matrix. Here is a Heaviside function. So this matrix, which means that we have 1 when we have time in the trajectory that 2 points come out with each other, it means 1. Otherwise, we have 0, and we represent that in a graphic. And this graphic is what we call the recurrence plot. For example, again, we have the Lorentz system, and out of the trajectory in the state space, we have points 1 when they are come to each other. Here's the time, both time, and we have this graphical representation out of that. So, for example, if I have a system, here is actually the oscillator system. We can see the recurrence plot came out. And when we have points that are close to each other in the epsilon distance, we point points representing that they recur, they come close to each other, okay? So this is a very nice idea that allows us to represent, to come out to recover this idea of recurrence. Over the time, a lot of work has been done in this area of recurrence. And we now know that out of recurrence, we can get the basic invariance of the underlying dynamical system. It means that out of this, we can take the information that are invariant for the system, like entropy, Lyapunov exponent, and dimension. And we are going to take that also in our methodology to come out with the relation between underlying systems and measure time series. First of that, let me introduce you this concept of probability of recurrence. If you have, for example, our recurrence matrix with 1s and 0, and if I take, for example, the time, and or the value in the one time, I can measure the number of 1s or the number of points that the recurrence happens out of the number of points that I measure, and we can up with the probability of recurrence at a given instant of time. And also, this concept can be extended if I wanted to measure recurrence, simultaneous recurrence between two different trajectories of two different systems. It means we just multiplied both of them, both of the recurrence metrics, and I came up with a measure of when we have two systems different that on time they recur at the same time. It means out of this I can get information like synchronization, or correlation, or whatever. And out of this information, I can have the joint recurrence probability that measure when I have on time for the system that both of them recur at the same time. I can have this probability that I can have for all the points in my trajectory. So, out of this, we can introduce, actually these guys, Norbert Marvan and Golse, introduced this concept of recurrence-based measure. It is based on mutual information that people use it to get out relation. And for this kind of mutual information, they actually just take into consideration the information conditioned to the previous variable, and they measure the reduced of information when we have the condition of the past of the present variable. And we can do that not in time, but in the recurrence plot, using the recurrence matrix and introducing the concept of probability that I have shown to you before. So this is the main idea. So out of this, I can find out when one variable influences to each other. However, this have a problem, because it cannot distinguish if this relation is due to autocorrelation of these potential driving variables. Here I have the driver, here I have the driving, and with this measure, I can have, considering not correctly, autocorrelation of the driving variables. So, how can I solve this problem? Because this idea is very used nowadays in different areas. So, to do that, I'm going to remind you this concept of Granger causality. Granger causality was introduced for Granger, who wins the Nobel Prize in 2003, and he said, in general, the following. If I have an X variable or an X system, And if U is all the information of the universe accumulated in the past, and if this I take out the Y, or it means all the information of the universe with the exception of Y, and if the standard deviation of forecast X is decreasing with, if I take out this Y, that we want to measure, it means that this Y actually is influentiated X. It means that it's causing X because of Y. Though this is the concept of Granger causality, actually this is a linear concept, and allow us to find out correlation, who is influentiate to each other in a linear sense. So we can extend this approach using the kind of transfer entropy. And what is here is in this formula is that we do that, but take in consideration previous information of the driving variables that you want to measure. It means, actually, we don't want just consider the driver information of the driving, but we condition this information to the past values of the driving. So doing that, we can somehow find out if this X is really a driver for Y, taking out previous value of the driving value. In this concept, we can use that. It means that here, we take out previous influence of the variables that we wanted to see if he's influentiated by the X, and just consider the influence of X of the previous variables. This is what this expression means. So we take this idea and put in the framework of recurrence plot, using this information of probability that I showed to you before, and we got this. It is recurrence measure of conditional dependence, that is this idea of get this measure, the reduced of information, the concept of recurrence plot. So it quantifies the recurrence information shared by the past of the potential driver in the presence of the potential driving variables, while conditioned to the past of the driving variables. So we consider the information of the driving, and we condition that to take out this previous information. By doing that, it rules out any self-influence of the driving variables, and it ensures non-symmetrical properties that reveal direction of coupling. Because with that, we take out the symmetry, and we are able to find out the direction, who is exactly influentiate the other. And it's not bidirectional, it is just in one direction. So in order to show that this really works, we use several experiments and also synthetic data. For example, here I have an ARMA model, and we see here that really Y influentiate X, you can see here, 10 times before using the lag, considering the lag. Here, actually, our confidence interval, it works fine. And also, we can see that by doing that, we can take out indirected influence. For example, here, the standard map will tell to us that X is influentiate Z, which is not true, because actually what's happening is X influentiate Y, Y influentiate Z. And you can see with the previous measure that was used before, it showed wrongly that actually X influentiates Z, but with our approach, it shows that there is no disinfluence. It means it rules out indirected influence, which is very good for this kind of recovered interaction network. And actually, for example, here I have a more sophisticated system of two Lorentz systems. There is a continuum on time where we are able to find out exactly who influentiate each other and which time in the past. That means the lag of information. So now, an application on that. We applied this approach to find out one very important or extreme events that happen in Amazon. The drought that we have here, we have the Brazil, the climate issue, we have the Amazon here, you know, it usually to rain a lot. But usually you have this scenario. But in 2005 and 2010, we have a very, very, very extreme drought in Brazil, we saw before, he's here. Now we have the scenario. It happens in 2005 and 2010. And also in the Cantareira, the main water reservoir that supplies São Paulo, and in 2013, in 15, it has a very strong draw. So our question is that, for example, if you take this 2005 and 2010 draw event, they are the same. They are causing but the same. For example, people used to say that this phenomena is caused by El Niño. Is it true? We found out the following result, that actually in 2010, El Niño was responsible for the causing of the draw, but not in 2005. Actually, 2005, we reconstruct the network of climate interaction, and we found out that this was caused by the surface temperature of the south of Atlantic Ocean that was very hot, that was above the normal weather, and then it caused the drop in 2005. But in 2010, actually, it was El Niño who caused this problem. So this is what we got about this. And this approach was used in a lot of experiment data for brain, for neuroscientists, for climate. And it's based on transfer entropy definition, explore the joint recurrent plot concept. It's very fast. It can handle noise data. It works very nice even with noise data. It works properly to unveil causality interconnected system, which is very important. It's easy to implement. It's not computational intensive. This work was published in 2017. If you want to see details about that, you can go to this paper. Thank you so much.
All right, we have time for a quick question. In terms of the time series length, how does...
There is no limitation for that, because we compute recurrence. We can do that with very long time series, and if you can divide that on parts and you work properly with no problem, and it's very fast.
I guess I was thinking about the opposite problem, so short time series. What,
do you have a sense about on the short length? Time series, actually the problem is to estimate probability. And in terms of climate, you know, we do not have much data because you have one measured date. But we found out that even in this case, with short time series, it worked properly. It was able to show the results that are consistent with what we're thinking. We just finished a paper showing this result with the synthetic systems like ARMA and Lorentz system. And we show the minimum amount of information or the length of the data series that you need to use in order for this to work. But it looks like it works properly, even with not extended time series.
Great. Any other questions? All right. Oh, yes.
So you showed this matrix so that it was discrete.
Yes.
And we normally think of chaotic systems as continuous.
Yes.
So I was wondering if you were looking at each trajectory as
No,
a
no, no.
discrete
We have
entity?
one trajectory. And out of this trajectory, using the recurrent plot, we came up with the recurrence, actually the recurrence matrix. And we use this matrix to determine the probability, and with this probability, we are able to implement our methodology. Okay? So we move from space, from the time space, to the recurrence space. You can say that.
Great. Well, I think we'll need to move on because it turns out the third speaker is actually here. So with apologies to the fourth speaker, you're now back in the original position. Let's thank the speaker one more time.
Thank you. Thanks so much.
Okay, my name is Jarosław Jankowski. I'm representing our research team from Rensselaer Polytechnic Institute and from Wrocław University of Science of Technology in Poland. The presentation is related to sequential seeding and this method of spreading information over networks. The plan of presentation includes general areas related to information diffusion, seed selection methods, presented approach related to sequential seeding, coordinated execution approach, and experimental setup and results from our studies. The area of information diffusion is related to several aspects, to ideas and innovations, to economy, to marketing, and especially is visible within social networks, online social networks, and even this kind of areas related to rumors and spreading information was analyzed many years ago. Together with development of electronic systems, it is possible to detailedly analyze spreading of information, monitoring it, and analyzing the performance. General approaches can be based on broadcasting of information and analytical models without taking into account structure of networks, and network-based approach where we can analyze connections, when we can analyze the cascades and routes of spreading information. We can see several targets of information spreading methods. First, we would like to achieve the highest possible coverage within the network and the high fraction of audience to attract with new information, with new products. So it can be main target of campaigns. Other target can be to lower dynamics of information spreading, like for fake news or computer viruses. We would like to stop spreading and suppress information spreading. But from the perspective of increasing the performance of information spreading, what solutions we can explore? The easiest would be activating all nodes within the network, like company would like to give product sample to launch and increase information about products. The simplest would be giving product samples to all members of population, but it would be very costful and we would need unlimited budget. Then the main target is to select the minimal possible number of number of users with high possibility to spread information about product, and infecting only n seed at the beginning. It is the main strategy now. So we are trying to decrease our budget and make possible high number of activations within the network. And several seed selection methods are explored. There are focused on some heuristic measures, on greedy approaches, and other solutions with ability to select nodes within the network, like PageRank, VoteRank solutions, and other methods for seed selection. We can use here several network metrics, homophily, and other phenomena within the network. But seeding strategy is essential for the final coverage. If we have good strategy and we select proper nodes within the network, we will have bigger chance to attract the high fraction of nodes within the network. The most common approach to seeding is single stage seeding, where we activate all selected seeds at the beginning. Let's say we want to give our product sample to 100 of customers. We are selecting them, giving them a product sample, and now we are observing results. if they are spreading information among friends, if they are adopting to new products. So it is kind of single-stage seeding. But with the use of this approach, we don't have the control over the process. Process is starting, information is spreading, but we are not intervening. We don't use gathered knowledge about the process to improve the process. So this kind of approach is not assuming any adaptation to observed behaviors. But from another areas, we know that we should not put all of eggs in the one basket, so it is similar to seeding. If we have 100 of seed and we put them into the single audience or single community or single area of the network, we have the risk that this region will not work properly for us, will not spread information. Then this kind of rule can be applied to network science, and we did analysis and some research to sequential approach, which is common in another areas as well. General theory of decision making, sequential decisions. When we are decreasing our uncertainty about the problem, we can divide our bigger decision in several stages. In financial markets, we don't need to invest all our funds into single company. We can spread our investment over the time. We will decrease the risk. And seeding real plants, if we have 10 real seeds, if we put them into ground, if here is a desert, we will see no plants, no trees, and all seeds will be wasted. And when we look into sequential seeding, the main idea is to split seeds into the over the time and use only limited number of seeds and during the process. And if we compare single stage seeding like here, we have 6 seeds denoted with red color. We are taking them from our ranking by degree. We are activating seeding nodes, and they are spreading information to neighbors, to other nodes denoted in blue color. And in sequential seeding, we are selecting only one node. He is spreading information. We are waiting until the information spreading dies out. Then we are selecting another node, and another, and another. We are still using 6 seeds, but like on this ranking, we can see that first seed in the single stage approach, number 1, 2, and 6, we would use as regular seed. But in sequential seeding, nodes with the numbers 1, 2, and 6 were infected by other neighbors. Then it was not necessary for us to seed them because they were activated during natural processes, and we could activate because of this saving nodes with number 24, 11, and 22. And because of this approach, it was possible to infect 24 nodes within this simple network instead of 16 infected nodes. We have here same network, same probabilities, but just spreading seeding over the time allowed us saving some nodes. And we explored and analyzed several sequential seeding strategies to see what is our real benefit from this kind of approach within simulated artificial networks, real networks with different probabilities, different structures. And we see here several possibilities. One of possibilities is sequential seeding with revival mode with most atomic approach, where we will use only one seed per one stage. So we are using only one seed, and we are observing cascades from this one seed, and we are waiting till the process dies out. Then we are using another seed, another cascades are launched, and over the time we are using all assigned seeds. In this example we have 10 seeds. Advantage is that we are using the potential of natural information spreading processes, but it can take a longer time. And to analyze this approach within several networks, several methods, we propose here a coordinated execution approach, which is another approach to making simulation over the networks. In typical approach, we should repeat simulation within the network, then make average values from results. Another method, if we test, we will make another, let's say, 1,000 of simulations, make average values. But the problem is that with very big experimental space, billions of combinations, if we repeat process within the network, it is repeated within completely different conditions. Different probabilities will be generated, and the process will go different paths, different cascades, and it is not easy to compare the process. In coordinated execution, we assume that we launch processes within identical conditions, and before executing the process, we are saving probabilities of transfer of information to each edge within the network in two directions. And if we repeat the process using different method on the same settings, we will have identical values transmitting information from node A to node B and from B to node A. It was described in paper reference number 1. I will show this at the end. And experimental setup. In experimental setup, we use independent cascade model with real and synthetic networks with various propagation probabilities, several sequential strategies, and how it looks. We performed a complete experiment in first stage of analysis with a small network where we were able to compute maximal coverage and optimal seed set, and we compared it with greedy single stage and greedy sequential. If we got seed set from greedy approach and we use it sequentially, it was possible to improve results like here. If it is interesting that if we got simple degree-based seeding, and degree-based seeding performed sequentially delivered better results than single-stage greedy results. So simple heuristic was able to deliver better result than greedy approach with a high computational cost. For comparing in pair greedy sequential and greedy single stage, we see that all results from greedy sequential are above greedy single stage. Same with degree. Single stage degree delivered worse result than sequential degree, and distances from sequential approach are covering our space to maximal results denoted by orange color and this line. So we are filling with sequential seeding space between our reference approach and maximal value. And using coordinated execution was possible to evaluate the gain. What is our gain? Gain is between results from traditional approach, single stage, and our maximal. So it is the distance where we still have some space to improve our results. And as we see, our gain, it was possible to achieve even 60% from outstanding space between traditional approach and maximal approach. And without coordinated execution and referencing values, it would be rather impossible to compute gain, because we have different results from different simulation, different randomized approaches. And detailed results described in paper are related to different used networks, more detailed analysis of results. And for example, if we have important is trade-off. We are in figure D. We see that blue line representing single-stage approach is reaching number of infected nodes about 3,000 after few steps of simulation, but green line sequential 1 seed per stage is reaching higher, but it takes longer. So it depends what is our strategy, what are our needs. And duration of the process, we can decrease duration of the process. If we use 2 seeds as stage, process will be shorter, but performance will be not so good. And sequential effect can be different for different network. If we had dense networks, we can get greater gain. And this proof for coordinated execution shows that sequential seeding always provides at least as good coverage as traditional approach for the same conditions with the same probabilities. And during these studies, we found another challenges like how should be spreading seeds over the time? Should we spread them equally? We have another work related to strategic distribution of seeds to supporting, published in PLOS ONE, when we used different linear distribution of seeds, geometric and Gaussian distribution of seeds over the time. Another approach related to this area is based on multi-criteria evaluation of the process. What is our expectation? What are our preferences? Gather a more number of nodes in short time, or maybe time should be can be longer, but we can get better result. If we infect nodes with very high degree, it can be more costful than infected nodes with medium degree. And what are our preferences? What are our budget? Another study was related to multi-criteria evaluation of effects of viral campaigns. And some real examples from virtual world were related to supporting campaigns where we have primary campaign. We are using smaller supporting campaigns as other seeds. And if we can increase dynamics of low-performing campaign with supporting seeding. And another challenge was related to recomputation of network rankings during the process to gather more knowledge, more knowledge during the process. And open questions are related here, and same like we saw at the first presentation of LADA, related to overseeding within the network, limit the number of seeds, and get enough number of results. And this work was related to several areas, published in few papers during this project, and you can find within them more details or within this presentation, which I can share. And remember that don't pull your seeds in one stage because you are screwed. So thank you very much for attention.
Time for one quick question, yes.
Thank you. How much do your results depend on the diffusion protocol?
About diffusion product? Protocol. Ah, protocol, yes. Our approach was based on independent cascades model. So information spreading was based on cascades, and we used flat probability for all seeds within the network. And it was kind of simplification. But if we follow these results from this paper and this proof related to coordinated execution, if we work within the same condition and same probabilities, actually it doesn't matter what kind of, if we use linear threshold method, we should get similar results because if we spread seeds into the sequence, we will always better results than better or equal result to single state. So we still see some opportunities to verify other models.
Great. All right, well, let's thank the speaker.
Thank you very much.
All right, now we'll have the last speaker for the session before the coffee break.
So this is microphone. Okay. Hola, buenas tardes. My name is Hite Kim, and like J-I-T in Castellano. And I think I'm supposed to start like about 10 minutes ago. So, and I know that there are coffees and snacks outside, so you guys don't imagine how I feel. Like I feel like to finish it very early than I expected, so I try to do my best. So today I'd like to talk about some story about power grid. So you're watching some video of the blackout happened back in 2003 in northern eastern the US. So it cascades so huge and affects the society, and it causes economic damages and inconvenience so big. That's not the story of the others. Actually, in Santiago here, like 2 months ago, there was a sudden blackout, and there was no traffic lights, and people had to walk or take a bus instead of using metros, and there was a huge accident. So people was spreading the news and give some information to respond how to do it. And actually, one of my friends asked me in Facebook that because I'm doing some studies about power grid, he asked me, so you guys, you know something. So what is the clue and what's the reason? So I answered it, no, I don't know exactly, but I'm trying to do my best. And he asked me, is there any guy asked you about this happening? Nah, nobody. Because we are network scientists, so we are aware of some topics in this area. But actually to the public, they are not aware about what's going on with these issues. So today I'd like to give some image or some idea about what I'm doing, how I approach to the power grid issues with network science. So to solve this problem, let's do the network science. So to do so, we need some ingredients, because power grid is a real infrastructure. Anyhow, we have to convert this real structure to a simplified network structure, and then we can analyze. Actually, it is a very active project. So in Germany, there is one institute try to the best to convert the German power grid to a well-organized network data set. And there is another project, ENSO-E, which is a pan-European project. They are converting all the power grid information to very well-organized data sets. So to convert it like them, we have some protocols. we need to set some protocols. So this is some diagram of the real power grids. There are power plants, substations, and some transmission towers that they don't generate or consume. They just support this grid as a physical structures. And after that, there is a distribution network to the houses. But when we mention about the power grid, it usually considers only this transmission network, regardless of this distribution network. So we have to collect information about this huge information and connect them as a network like here. As you see here, this is a power plant, so they generate electricity. And this line is just hang on another lines, which is called tap. So actually, this structure is a real structure of how the power plants or some branching line is connected to another line. So when we convert this physical structure as a network itself, it should be probably like this. So we can call it tap embedded structures. So this yellow dot, yellow node means the tap point. Doesn't produce any electricity or consumes, but has a physical role. Since we don't care about this meaningless node, maybe we can handle this structure to eliminate this tap structure. So there could be a second version. And this tower doesn't play any role in terms of dynamics. So they used to eliminate this node as well. And since this transmission tower connects the connectivity between these three nodes, so instead of using this, we can use this triangle shape, which is called the Cron reduced structure. So you can produce three different versions of networks. So this is the ingredient. This is the real connection structure of Chilean power grid. And it shows from the north to the south, and each individual power plants and substations. And it contains really amazing information, like how many power plants and what size of what capacity of the substations, transformers, something like that. So we use this information as one source of ingredient. And to know the geographical coordinates, we use another source. So this one is an example. And from the Chile, they have the type of power plants or substation and connection, capacity, everything. But it is not perfect, because when we more do the zoom in, the structure, the lines are connected to this substation. This is one example. But the connection points are different. So we just can simply consider this one as a node. We have to manually look into every details and convert these individual dots as a one big substation node. So this is a completely manual work, which costs a lot of time. And of course, these data are made by humans. So you see here, the connection is disconnected. And there is a node is separated from the branch because they made a mistake to type in some numbers when they made some digital files. So it requires a lot of effort to actually convert from various data sources to a network structure. Costs months of time. So as a result, anyhow, we were successful to generate the three different versions of Chilean networks containing all the locations and activity data and their unique characteristics. So we have a network. So let's analyze it. And what can we analyze? We were interested in the synchronization stability. So what kinds of synchronization issues are there? Actually, we are mostly using the AC currents, and there is a fluctuating current flow. So the frequency at each node should be synchronized like 50 hertz or 60 hertz in each countries. And for example, there are two nodes, and it is easy to get some external perturbation to each node. So if the perturbation is small, this is a frequency, they can recover their synchronization, the desired state. But if the shock was too big, they break into desynchronized states. So this is what we want to avoid. So we can use one dynamic equation, so-called second-order Graph model. And this P represents simply the amount of input or output, consumption or generation of powers. And K means the transmission capacity. So how much electricity can go through each transmission line. And A has the connection information as a adjacency matrix. So simply speaking, we can use this equation, this dynamics, to simulate what is going on these networks. So we want to estimate the stability. So the idea is simple. This shows the phase space of each node, over one node. And this is the phase, and this is a frequency. And this central black dot represents the steady state of the system. So when a perturbation was given to this node, represented as a black dots, it can recover their synchronization. So that's okay, without problem. But sometimes if the perturbation is too large or matches the specific situation, conditions, it fails to recover the synchronization and fall into the limit cycle. So the idea is that let's simply measure the area of Bayesian traction and interpret it as the stability of these nodes. And please note that this synchronization stability, called Bayesian stability, is a nodal index. So we can measure the stability of each node. And it means that, for example, the Bayesian stability 1 means that the node is always stable, meaning that if any perturbation is given to this node, the whole system always recovers the synchronization. So there are a lot of studies using this Bayesian stability to analyze the stability of power grids. And this is one example. The more yellow is the more unstable, the more bright is the stable. So we are interested in Chile, so especially this region, because most of the populations are saturated in this area. So this is one trial of evaluating the Bayesian stability or synchronization stability of Chilean power grids. As you can see, these nodes are very stable, but most of nodes looks very unstable, less stable. But I didn't believe it because I don't believe that we are living in this very unstable system, so there is something wrong. So I tried to tuning some parameters. Remember that the K represents the transmission capacity, the edge weight between each node. So I tuned the K values. So surprisingly, the result changes abruptly. You can see these two examples that shows they are very stable almost over. But the difference between those examples in terms of K is 10 to the minus 4. So we thought that instead of measuring with one specific K values, it's better to see whole the picture of how the system changes, changing the K parameters. So this was our idea. So this is the network structure, and the x-axis is K. So maybe we can change K and measure the Bayesian stability, change K, measure the Bayesian stability again. But according to the K values, their Bayesian stability could be different, and we can interpret the whole transition shape of their Bayesian stability. And we call this width of the lowest k value and highest k value, where the Bayesian stability shows 0 and 1 is the transition window. So this is the example. Maybe I can click here. The window is on my computer. I have to move it to right. Excuse me. So yeah. Here. Oh no. Okay. So this is a Chilean power grid, and let's say this x-axis shows a k parameter, and this is how the Bayesian stability changes at this node. And this node looks like this. So they shows gradual increase of their Bayesian stability, synchronization stability in terms of the k parameters. But one node in these clusters, like this one, it just changes abruptly. And another node has really many degrees, and it changes rather rapidly. So we were interested in the relation between topology and their transitions. So how to see, how to interpret the topology? That was the second question. So think about the relationship. Let's see this one example node. And this 8th node is located in the central area. So maybe these nodes are playing some role interconnecting these two clusters, and these nodes as well. When we consider only degree, it has some information. And to interpret the relationship, we can measure the between centrality as a basic unit. But as you see, since the shortest passes goes through only node 8, the betweenness of these nodes are rather very low than this central node. So we try to detect the community like several times. We use the Leblanc method. So the idea is that let's measure some community detections and use the stochastic, the degeneracy as a measure of information. So we counted how they co-current between each node. For example, from the each runs of community detections, how many times of these nodes are identified as a same community with this node and this node and this node. So here, this matrix shows how they are identified together or never together. And we interpreted these informations to identify community inconsistency, meaning that high community inconsistent nodes they don't have clear friends. Every time we measure community, their members are changing. But low community inconsistency means that the nodes are very consistent. So it is embedded in a cluster very strongly. So it has a very strong relationship. So we can use this measure community inconsistency to some networks. So to get some ideas, we tested some example networks. For example, this one is the famous Chakri-Karade networks, which is associated with some trainers that are separated into 2 big clusters or 4 small clusters. And this is the Star Wars trilogy, and we can identify the community into 3 different communities. And the size of nodes represents the degree. So it is understandable that why these nodes are big. And there are 3 clusters from Imperial Military Army, Resistance, and Jedi Knights. So this is what we know. But when we apply the community inconsistency, the very high inconsistent node is only this node in Faraday column networks, because this network is located into two different networks. So we can imagine that maybe this guy has a confusion that which community is my party? I'm confused, or not. Or so, in this case, the Luke Skywalker has the highest community inconsistency, because even though it has many degrees, their counterparts are assigned in different communities. So in terms of the identity of community, Luke Skywalker has very diverse association. So this node has a very high community inconsistency. So we have to be very careful to interpret the numbers, the value of community inconsistency. But in this case, maybe you can use it to identify some outliers or very multiple players. So we tried this measure to the Chilean power grid, and you see there are rather clear three communities, and these regions, their community memberships are frequently changing. So surprisingly, this community, the transition window is very positively correlated with the community inconsistency. So we interpret these results as so this is, we are talking about synchronization, how they will recover their synchronization. So they have to spread their shock to the surrounding nodes to recover their synchronization. So we think that if a node has more close friends, more frequent and closer network nodes in a network, is more likely to recover the synchronization. So we think that that's why the transition window is very positively correlated with this community inconsistency. So, but this is rather massive, because this is just one example of real networks. So we wanted to see more the fundamental of deep structures or simple structures. So we started from the very simple structures like this. So depends on the topology. Topology means the connection and the location of generation and consumption. The patterns are changing frequently, very differently. So we tried many motifs with number of 4 or number of 6, and found that some interesting patterns according to the topology. And this graph shows that when time passed enough after they got the perturbation. Yeah. So what we found is that there are some multi-stability. So this is almost all. And I'd like to thank my colleagues about our co-work, and thank you for your attention.
So unfortunately, we're over time, so we'll have to take the questions to the coffee break. I'm not sure what the plan is, Leo, for the break, because we're over time. But let's thank all the speakers again for a very enlightening session.
Thank you very much, Sam. Thanks. So we now go for a break. We do have about 25 minutes, 30 minutes, but I think I will have a nice surprise, and we'll cut it off earlier today. So we will see. We will see. But yeah, please go and get some coffee, and then come back in about 25 minutes, please.
Okay, can you hear me? Okay, perfect. Yeah.
I don't think they can hear you.
Hola. Bueno. Okay, so we're going to start the next session that is about social networks, and our first speaker is Tamas David Barrett. He's from Oxford University, and he's going to talk about demographic transition reduces social network. Please welcome Tamas.
Thank you. I actually have several affiliations. One is in UDD, here in Chile, and then some others. Okay, so do you guys, when you were kids, did you ever play Spot the Difference? You played Spot the Difference. You know what it is, yeah? So I'm going to show you two pictures, and please spot the difference. Cool? Okay, so this is the first, yeah? This is the second, yeah? You recognize what's going on here, yeah? So the first is Queen Victoria, yeah? With her children and grandchildren, and this is the Queen's mummy, the Queen Mother, with her children and grandchildren. So what's the difference? Did you put your hand up? What's the difference? Huh? The number of kids, yeah? So Queen Victoria had 9 kids and 23 grandchildren, and this photo includes great-grandchildren as well, who were living at the time. So what happened here is that suddenly, from in 100 years, the number of children born to women has collapsed. So what I'm going to talk about today is how this change in the number of kids, this demographic transition, then affected the social network that people live in. Okay. Right. So this is a stylized fact. Hunter-gatherer populations have about 4.5, 5 kids per woman. Usually, the scheduling is completely different to modern populations. Usually, women have the kids earlier, and at one point, they stop. With agriculture, this had gone up to 6, 7 kids per woman. So agriculturalist populations have a very high number of kids. And then, about 300 years ago, in France, this very high fertility rate started to drop. About 100 years later, early 19th century, Britain and then other West European countries caught up. We have proper global data from which we could calculate the global fertility rate only since 1960, at which point it was 5.2 kids per woman. And now, it's 2.5. Never in the history, including the, as far as we know, the evolutionary history of humans, has the fertility rate been as low as it is today. And this has a big consequence. And the reason is, oh, I've got this. So the reason is because when you have fewer people born, you have fewer relatives. So look at this. Here's you, then your parents, your grandparents, your great-grandparents, and this is going to define a tree that goes to your second cousin. if you look at how far hunter-gatherer populations account in terms of relatives, the average is to second cousins, with actually a surprisingly narrow range. So we could say that the human baseline is accounting relatives to the second cousin. But there's something else is going on there, because you have a partner. And with your partner, you have in-laws. And when you have in-laws, suddenly you have a lot of new edges. Because it's possible that your sibling, recognizing your partner's sibling as a sibling in-law. So there's a new network edge appearing there. And it turns out that people all around the world, in traditional societies, like to populate their social network with relatives. We have properly mapped, so far, only 4 hunter-gatherer populations, hunter-gatherer cultures. And what we see here is that all of these are either direct kin or distant affines. Affines are the in-laws. Here, this much. Here, this much. Here, this much. That means in an average hunter-gatherer group, you are going to live together. It doesn't even include the actual social network. These are very small groups, so everybody's really a social relationship with everybody else, with about 3/4 of your relatives that are relatives to you somehow. And that preference has a consequence, because then it will determine how many siblings you could possibly have. So for this thought experiment, let's assume that mortality is 0, which is, of course, not the case. But let's just assume that for now. So if you have a fertility of 5, which means 5 kids per woman, how many siblings are you going to have? 4. Thank you. Well done. OK, how many cousins? Oh, smarty pants. Suddenly, like, how many cousins? Give me a number. You've got 40 cousins. Yeah? 20 on your mom's side, 20 on your dad's side. So that's 44 relatives in the same generation as you are, and we only accounted to first-degree cousins, not second-degree cousins. Yeah? So that means that if all of them get married or pair up, marriage is really an agriculturalist concept, then you've got 88 relatives altogether. So you've got a lot of people to populate your social network with. So what's the case when you have fertility 2? 1 sibling, 4 cousins, altogether 5 sibling in-laws and cousin-in-laws, so 10 people. So that means that when fertility falls from the baseline 5 to 2, and most Western populations, the fertility now is well under 2, you have from 88 to 10 people in the same generation as you are to populate your social network. So that means that if you want to have relatives in your social network, you're running short. So the question is, what's going to be the consequence of this? So when a society goes through demographic transition, how does this affect? Does it affect at all the social network? So let's assume a little thought experiment so that let's say that Fran, as a volunteer, has 2 siblings, Leo and George. What is the relationship between George and Leo? They're siblings, they're brothers. By definition, they're brothers, putting aside paternity uncertainty. But let's say, about 2% of humans. Let's say that we have another set of people. János is friends with Jesse and friends with me. What is the probability that Jesse and I are going to be friends? Less than 100%. And that's basically the insight. When we replace relatives with friends, the clustering coefficient is going to fall. Okay. We see 5 vertices here. What's the degree? 5. It's uniformly 5, yeah? Here's another graph. 5 vertices. What's the degree? 5, uniformly 5. Yeah? What's the clustering coefficient in the first? 50%. What's the clustering coefficient in the second? 0. That's my talk. So what I did is I built up some simulations, simulated historical populations, and I grew societies with fertility 5 all the way down to 2.5. The reason not to 2, because at that point, because of the randomness, it keeps breaking, but say 2.5, and 2 population sizes, 500 and 2,000. The reason for the 2 population sizes is that in demographic transition, mortality goes down first, and then 1, 1.5, sometimes 3 generations later, birth goes down, fertility goes down. So of course, because mortality had gone down before, the size of the population increases in between. Yeah. So in demographic transition, we have 2 effects. One, fertility changes. It goes down from high to low. And the other one is the size of the population goes from small to large. It turns out both will have an effect. We will assume that everybody has a fixed number of social contacts. We will assume that it's 60. Yeah? We have a lot of data that shows that the number of meaningful contacts might vary a little bit. It varies within our lives, varies across populations, but it's within a range. I can talk about later what happens if we relax this assumption, but let's just stay with this now. And then we assume that if you run short, if you have relatives up to first cousin, you will use them to populate your social network. And if you don't have relatives, you choose someone random to be your friend. And this is what we have. X-axis is the number of relatives. Yeah? So from 10 to all the way to 60. Yeah? At 60, we set everyone's number of social contacts at 60. You cannot have more. If you have less, we will fill you up with random others. Yeah? So this is when the fertility is high. This is when fertility is low. The blue line is a small group. So this is the results of 400 simulations. Yeah? The blue is a small groups, 500 groups. The red is a larger group, 2,000 groups. The y-axis is the clustering coefficient. So what we see here is that during demographic transition, in this model, the clustering coefficient collapses from a very high level up here, yeah, in the blue line up there, to an extremely low level, to red that line down here. Will have a bunch of consequences. Another side effect of this is that you will have the group size, depending on the group size and the fertility, the graph distance changes within the group. It's tricky to tell, of course, where we are going to be, but here's a more meaningful result showing the same thing. This is group size 500, group size 2,000. I'd like you to focus on the 2,000 now. This is, again, the number of relatives you have from 60 all the way down to 10. And this is the number of contacts you have who are 2 or 3 steps away. These are the 2-step away contacts. No, this is a two-step away context, and this is the three-step away context. Yeah? So 1 step away, 0 step away is how many people? 1, it's you. 1 step away, it's 60. We fixed that. Yeah? So what we have here is that if you have a very high fertility, you have a lot of people 3 steps away, and quite a few 2-step away people. As fertility falls, as fertility falls, this turns around. So you have a completely new phenomenon. Suddenly, the majority of these populations are going to be friends of friends. Another interesting thing is going on, that we humans use 2 tricks to enforce norms and reduce free riding in our traditional populations. One is the classic inclusive fitness solution that was discovered by biology. We like to cooperate with our friends, with our relatives. And the other one, discovered by economics 20 years after the first, was reputation. Either reputation within a reciprocal relationship or a reputation in a network. When we build kin networks and we do our collective action on kin networks, we use these 2 tricks. Every traditional society, without an exception, uses these two tricks combined into organizing collective action on kin networks. But if you don't have relatives and the clustering coefficient goes down, suddenly neither of these 2 works. You can't really cooperate in a large group of relatives because they're just not there. And the reputation path doesn't work because the clustering coefficient is low, so you can't actually tell if somebody is free riding. Let's say I am free riding on something. Yeah? Leo will tell Fran, this guy is not okay. Yeah? As long as they are connected to each other. If they are not, and I know that this effect is there, so I will not free ride. They are not connected to each other. I will cheat on Leo, I will cheat on Fran, because the cost of cheating had just collapsed. So this model does exactly that. So looked at assuming that everybody is a cooperator and one person cheats, which is a randomly chosen person. How long does it take for this information to pass on in the network? This is the small group, high fertility, starting from this is rounds of passing on the information. So as we go on, spreads in the network extremely fast that this guy is a cheater. This is the high fertility, the low fertility large group. Look at what happens here. As fertility goes up, especially in a large group, the network-based way of enforcing cooperation goes away. So that would suggest that suddenly we need something else to generate cooperation. And obviously we know what, in these societies, cooperation is being ensured by the legal system and the enforcement system. Essentially institutionalized third-party punishers. But there's something else is going on. Because we know that the weakest part of that model was the assumption that people choose their friends random. We don't choose our friends random. Oh, you like Mozart. I like Mozart. OK, shall we be friends? Homophily, birds of a feather, friendship choice heuristic, is the strongest way of predicting who's going to be your friend. And when you take that into account, we have a different image. This is, again, the number of relatives from high to low This is, again, the clustering coefficient. I apologize, I swapped around the colors, and I realized that I would have to rerun some bits of, so anyway. So this is the original blue line, and this is the original red line. Yeah, so this is the, yeah, these are the two lines here. These two. Yeah. What happens here is that if you can replace the missing kin with those who are similar to you, I use an extremely simple thing. Everybody got a random point on a unit circle, and if you two were both looking for a new friend, a new connection, and you were the closest in both of you in the population to each other, that's when the link came up. Yeah, basic stuff. Look what happens. For a while, you might be replacing some of your relatives, but as they are, but still having this negative effect. And then, I apologize. And then, suddenly, the clustering coefficient goes up again. So it seems that people engage in friendship choices that will actually do this job. In fact, we have a bunch of homophily-inducing behaviors that is going to make sure that we have some kind of homophily. Let's say that Leo and Fran, they don't know each other, but they're my friends. I say, Leo, Friday evening I'm having a dinner party. There is this person that you two are gonna just get on like a house fire. Just come. What I'm saying here is that I'm giving you some incentives to show up and make a new network edge. But if you are dropping an old edge that breaks up a triad, they are going to be on the same level. There's no increase in their or decrease in their clustering coefficient. But my clustering coefficient goes up. Yeah? Here's a bit of evidence. So this is the birth rate in England and Wales. This is the average birth rate, not the elite. Yeah, the elite was earlier. Look at the time scale. Yeah? So much of it is the 19th century. And this is the London club opening year histogram. So which year, how many clubs were being opened? Yes? Question? 5 minutes. You're the chair, of course, yes. OK, I'm almost done. So we have a bunch of consequences from this. One is that if this is true, the small world effect might be a consequence of changing fertility. We might have a new explanation for where institutionalized law enforcement comes from. But there's something else, and this is, I'd like to highlight, I should have highlighted this. It is not only falling fertility when we run short of relatives. In an urban space, somebody else gets in between us and our second cousin. So we have a repeated meaningful interaction with somebody else. So urbanization would have exactly the same effect. Sometimes relatives get wiped out by war or epidemics. Sometimes we lose our relatives because we migrate and they stay behind. In all of these cases, you would expect the same phenomenon to appear. In fact, as far as we know, and I haven't done the study yet on this, legal institutions always appeared in new cities. Okay. And there's a host of psychological consequences. Social isolation. We sometimes replace our missing relatives with pets. And then the latest thing that we're working on, we think we might be able to predict what happens during adolescence. Because when you're an adolescent, suddenly the number of your connections, your degree goes up, but your clustering coefficient goes up, might be going up slower than your degree. And maybe some people are particularly sensitive to this, or some people just have fewer connections. And they might trigger some maybe adaptive response of depression and might end up in suicidal behavior. Right. So I thank your attention with a bonobo Venus. Yeah, thank you. Questions? Shall I? Do you want to? Do you have any questions or comments?
Yeah, we have time for a couple of questions. Okay.
Thanks for the very nice talk. Can you quickly comment on the assumption?
I can't hear.
Thank you for the very nice talk. Can you quickly comment on the assumption of the uniform choice for the degree that you have in your model? That's quite unrealistic. I know where it's coming from. But
yeah. So it seems one way it seems that something happened the last few decades. There's a lot of sociological evidence that the core got smaller. This actually came from originally from conversation group sizes. And it seems that conversation group sizes, they got smaller, almost as if you would pull the core towards yourself. With the social media, you have a weakening of so you can have a lot more of the far away, weaker ties. And of course, all of this would affect the result, yeah? Because this one, yeah. So if you allow the core to shift down, yeah, so that exactly you come in here, yeah, and if you allow the further away people, of course you're going to have different things. What's interesting is that I think maybe we have a super sophisticated response to this, because it might be possible to actually shorten the trough by reducing the core and at the same time increasing the further away bits. Yeah?
My question is just about this this figure. There is this minimum here, and
this.
Yeah. And I don't understand the reason, because why can't the people substitute their missing relatives immediately by friends?
Or they're immediately replacing them. But what is happening is that you are still friends with your relatives. So here, so at this point, half of your 60 are preset by them being your relatives. Yeah? The other half is the friends. So you are immediately replacing the missing relatives with friends, but you still have your relatives. One possible way of tricking this effect is you give up some of your relatives. Yeah? So again, that would be another way to reduce, the trough doesn't go away, but another way to reduce the trough is to actually, all right, I'm not going to do my second cousins. They're really weird. You know, my uncle comes to Thanksgiving, whatever, and you know, he gets drunk and he's supporter of this crazy president or something. Yeah? I'm not referencing any society. So it's possible to drop those. And again, you would reduce the trough. And of course, there's the model that we're working on, which is another way of reducing the trough.
Any other question?
No?
Okay.
So Thomas, this is amazing. I mean, the stuff is based mostly on models. Do you see what kind of experimentation would actually prove your point? Let's say, what kind of data would actually show you? What kind of experiments would you do?
Actual experiments.
Yes, actual experiments. So is there something at this time scale that would give you this kind of insight?
So the tricky thing is that people arrive into the lab with a preset social network, and it's very, very difficult to. So far we have been looking at data sets, and we can say, okay, can we? So I'm working with a lawyer or a legal historian. Is it true that it is urbanization and falling fertility comes in? Another effect which I haven't mentioned is that actually when the relatives reduce, that offers a space for ideologies that use kin replacement language. Yeah? Our communist brothers and sisters, Mother Russia, the Vaterland, yeah? All of these, a lot of religions, a lot of ideologies use this kin language all the time. The family, father, my brothers, so all of that comes in as well. If this is right, this will predict when they come in and when they get strong. And some of this is really very tempting, yeah, but it's not really science, yeah. So like, okay, is it possible that this would have a different kind of explanation for the rise of the communist and the Nazi ideology, which is the war combined with the Spanish flu. You could say that, France nationalism, again, you can tell these stories, yeah, that how fascism started to fall in France, and then maybe you have the revolution. So we can tell these individual stories. We haven't put together the whole thing. For an actual experiment, what we've been fooling around is that whether we can see some of these coping mechanisms being more important in some societies where might be in the middle. Yeah. So that's the only thing we have so far. Yeah. Okay.
So, yes, I think it's very, very interesting. Just thinking out loud here, you could design an experiment in which you invite participants to play a game in which they have a certain amount of relatives, like artificial relatives. Actually, it could be themselves, a relatively large group. But then for one group, you ask them to choose who they want to be friends with, but not show them features of themselves, like for example, like gender, or you don't show them anything. But on the other one, you actually do show them some information, and you can try to reproduce.
So you suggest that rather than creating relatives, you create a highly clustered, or you have differently clustered.
I'm thinking about that, yeah.
Yeah. So you would basically move around on only this edge and say, okay, we establish the rest, and then so you would say, we are moving here. Do we see the say friendship formation behavior varying from this point to this point? Yeah. Or at any one point.
Yeah.
That's a great idea. Yes.
People who have many siblings and study their effect in the network, because there are people
Yes.
who have 5 siblings
Yes.
who have a bigger proportion
Yes.
as compared to them, and different probabilities of propagation of things, etc.
Yes. It seems that people who have a high number of siblings, their total number of social connections actually a little lower. But so we have a Brazilian and a Dutch data set, but we have right now data set problems because some people have 5 mothers. So that's not published yet. Yeah. Okay. Great. Thank you very much.
Okay, let's thank Tamas for his great presentation. Our next speaker is George Vega. He's from the University of Southern California, and his presentation is Small Network Statistics for the Network Science of Teams. Let's welcome George Vega.
Do you need this? Yeah. And this is the okay.
Can you hear me? Is that okay? Okay. Oops, what's going on? Okay, so this is work that I'm developing together with Professor De La Haye at the University of Southern California. And I want to thank our group, CANA, Center for Applied Network Analysis at USC, members from the immunity team, and Andrew Slaughter, and attendees of the NetSciX conference this year. First things first, I'm supposed to do this, otherwise I will get yelled at work. So who are funding us? This is a project funded by the Department of Defense of the United States, and also supported by USC Center for High Performance Computing Center. Again, this is part of the immunity team's network science. Okay, so first things first, the context. So we have this experiment in the lab in which we basically recruited a bunch of individuals, exactly like 42 teams of networks in which we form groups of individuals between 3 to 5 members. They have to be over 18 years old, native English speakers, and we actually, they went through a 2-hour session in which they solved some problems. We asked them to work on some tasks, and then did some surveys to ask them about social network questions, for example, like who do you seek for advice, who do you trust, so on and so forth, and took some measures about the individual and social intelligence. And the thing is that overall, what motivated us is that we see there's a very limited set of on social intelligence that has been tested as predictors for social networks. In the terms that, for example, not many structures like, for example, homophily or other empathy or other stuff have been used from the network science to predict performance on social intelligence measurements. And again, so there's very little research on the emergence of networks in teams. So this is how our data looks like, for example. Here we have the set of teams of size 4. And surprisingly, even though we have like this very small data set, we do see some structure and heterogeneity in the data. So for example, we have fully connected graphs. There are some empty graphs, so on and so forth. So the thing is that we were wondering, how can we go beyond descriptive statistics? How can we go beyond just counting triads on motives and things like that and do some inference on this? One of the answers that we approach, we are taking many approaches, is looking at network formation. In particular, we're looking at what's called exponential random graph models. So how many of you here know about exponential random graph models? Okay, cool, a few. The thing is that when you're trying to estimate an exponential random graph models, basically the question there is to see what are the substructures, features of a graph that characterizes it the most. For example, whether it is number of triads, mutuality, a structural balance, or some other features that give origin to this network. And the thing is that, again, so when we are trying to estimate exponential random graph models, we usually have a single object, which is the graph, a single observation, and we try to fit this fancy model. The thing is that estimating exponential random graph models is not an easy task. For example, for calculating the likelihood of any given graph, there are exactly 2 to the n minus 1 terms to be computed, which means that, for example, if we have a network of size 6, we have roughly 1 billion terms that we have to compute every time that we compute the likelihood function of that given graph, which makes the estimation very hard. And because of that, nowadays, the most common approach to estimating exponential random graph models is using simulation. For example, Markov chain Monte Carlo and MLE. The problem with this is that when we try to feed these types of models using these simulation approaches, usually MCMC fails to converge. And we see even when we try to estimate what's called a block diagram model, in which, for example, we have all the 42 teams in a single adjacency matrix as a single network, and we try to estimate that fails to converge most of the time. And even, and the same happens when we try to estimate a little graph. And even if it converges, we have what's known in exponential random graph models literature, which are the degeneracy problems, which means that some structures cannot be fitted due to the MCMC getting stuck in some places on the sampling space. So it's a problem. And after we try a lot of times to fit these models, we actually start to think a little bit more, and I figured out, okay, so since these are very small networks, between 3 to 5, why don't we just go and do the brute force computation of the actual likelihood function? So that's what we're actually doing now. So instead of using the MCMC MLE approach, we take advantage of the size and go for exact statistics. So for those of you who have never seen it, this is how the likelihood function for the exponential random graph models looks like. So where theta is the vector of
parameters. G of y, in this case, is a vector of sufficient statistics. And here's the normalizing constant, which is the bit that has the 2n to the n minus 1 terms that is very complex to estimate. And by doing so, by computing this exact statistic, we actually are now able to solve the problem of estimating small networks, small ergons. And actually right now, so by the way, I'm like in a statistical computing side of things, so I think that for science, when you are doing this kind of stuff, you have to try to like develop software well documented so people can actually use your method and it's not lost on the archives or whatever paper you send it. We have an R package that we are working on that's called Largram, which stands for Little Exponential Random Graph Models, but we actually are going to change the name. And it's already available at GitHub. They're at our Muri team's website if any of you is interested in looking at it. So here's just an example. For example, we have here, I'm using this R package. I'm just simulating a Bernoulli graph with four nodes. And then I'm trying to estimate these exponential random graph models in which I'm including number of edges, number of balanced edges, a number of balanced triads, and a number of mutual edges. So we can fit these models now. So cool, we are able to fit these ergons, these little ergons, which we actually call ergomitos, by the way. For those of you who don't know, so in Chile and in Spanish, we have the etos, which means small. And I have to thank Professor George Barnett during the NetSciX conference who suggested the name very elegantly. So going directly to the MLE estimator, we actually now avoid the problem of the degeneracy in the MCMC estimation. So we can do things with these little networks. And moreover, due to the size of this network, we can actually go further and try to estimate pool ergons, which is great too, because that increases our power. One thing to notice, though, is that something that I recently became aware of is that asymptotic properties of exponential random graph models is not very straightforward. So one can think that, for example, having a graph of size 4 or 5 is not like a very large for asymptotics. But actually, asymptotics in exponential random graph models is a theme that is being highly discussed nowadays in literature. So it's not very straightforward. And so which means that it makes sense to estimate models in this case with such small networks. And the thing, so as I was saying earlier on, we try to estimate an exponential random graph models in which we have a block diagonal network, right? Which means that we have a bunch of, in the diagonal, we have a bunch of little networks. And then out of the diagonal of the adjacency matrix, we have a bunch of structural zeros, right? So that was essentially assuming that all these small networks are actually independent between each other. So that means that we can actually go and take all of these networks and do a pool estimation just like you will do with a logistic regression by multiplying the likelihood function of each one of these. Which, again, this increases our power for our MLEs and efficiency as well of the estimator. And we actually implemented this on the Largram package. So here's another example for those of you who have experience using ergons in R. Here I'm just simulating 4 networks of size 4, 5, and 5. And then I estimate this pool model by just listing them the same model, and it works, okay? Without having to do anything with simulation. So it's just straight Newton-Raphson optimization. So to see how this behaves, we actually did some simulation studies. We had 2 scenarios. The first one, we draw parameters of edges, mutuals, and mutuals. So these are the only 2 parameters that set the data generating process from a uniform -3, 3. Using those parameters, we sample n networks from a Poisson distribution with parameter 30 to yield networks of size 4. And then we estimated, in the sense that what I'm doing here is that I'm drawing, generating data sets that on average have 30 teams. That's what I'm saying. And each one of them with size 4. And then estimated the pool ergon using maximum likelihood, and then also the bootstrap version of it, just to make sure that we get the standard errors properly. And then in scenario B, we did kind of the same thing, but instead of using all of the networks in each sample data, simulated data set of size 4, We did some with different sizes, with sizes 3 and 4 respectively, from a Poisson, again, 15, 15. And we did the same, estimated ergoms. And if anyone asks, this means that we just ran about 3 million ergoms for the simulations. I know that for you physicists, this is not impressive, but for social scientists, they were like, oh. So, OK, so here it is, the results. We were mostly focused on the bias of our estimates. So here we have the bias distribution of the estimation of the edge parameter, and also the bias distribution for the mutual parameter. And as you can see, overall we're doing pretty well. Here we're not seeing the 2,000 networks that I generated, because I generated 2,000, because in some cases the set of parameters that I obtained generated either the empty graph, which means like no connections, or the fully connected graph, which is not very interesting. So that's why I dropped them out. I just kept these. And in terms of the power that we obtained for discovery of the parameters, as you can see overall here again, so using just on average 30 networks of sizes 3 or 3 and 4, we do have a very high level of power, which is very good news for those people who have small networks, this type of data. Again, and that was for scenario A. In the case of scenario B, we have kind of very much the same thing. We do have some outliers, but in general, we're doing pretty good in terms of bias. And again, power, pretty much the same story. Here, it's kind of, it's a little bit weird, because I think that in this case, we have only just 1 or 2 points that have that amount of networks. So this is the sample sizes. Here are just 2 that have like 60 or more networks in one pool ergon. OK, so that's related to the estimation of the power of the ergons. And another approach that we are taking right now that, unfortunately, I didn't put like a very good quality for printing this plot, but the thing is that we're also looking at ways of how can we compare matrices across. For example, we have a single network, a single team, and we computed what's called like the cognitive social structures, and went to compare within group the differences across these binary matrices. So what we're doing now is that we found this paper in which they have a bunch of metrics for calculating distance and correlation between binary matrices, and we implemented it also in another R package. So we are I don't know, we have roughly, right now we have like roughly 30 different metrics, other than, for example, the Hamming distance, which is the most popular, I would say, for comparing binary matrices. So we are doing that as well. OK, so for the discussion, first set of results, as you can see from the simulation, are encouraging. We're getting good power at low bias, which is pretty good. But again, also, this is under simulation, and every time that you present a simulation, simulations always look good, because they have to look good for your paper, right? You can't show bad results. So, but either way, it's still, I'm encouraged. We need to do some more simulations using null attributes at networks of size 5 and 6. Right now, I'm having problems with the data generating process, because trying to sample from a vector, trying to do a weighted sample from a vector of 1 million terms is actually not very fast. I thought it should be easier to do, but it turns out it's not. So I'm working on that. The structures imply that we have having smaller networks implies that we have a smaller pool of structures that we can actually test. But this can actually be fixed by using features of the graph, for example, for testing homophily and other interactions with features of the individuals in the network. And another kind of problem, not a very big problem, but we still have to look for, is that when we are estimating the pool version of these exponential random graph models, we are essentially hand-waving the fact that the parameter estimates implicitly encode the size of the graph. For example, does an estimate of h equals 0.1 has the same meaning for a network of size 3 to a network of size 5? There are some issues, and there's some literature that deals with these kind of issues, and we had to work on that as well. And finally, this can actually be extended to other types of small networks, for example, families, ego networks, etc., and other methods such as the separable exponential random graph models, also known as tergons. And that's it. Thank you very much.
Any questions?
Okay, good question. I mean, this is as much as a library, let's say, talk. It's very nice, actually. It's also an algorithmic talk. I mean, you know, where you've implemented this and stuff like that. What I was missing from a more computational point of view is about exactly what you said, like a little bit of asymptotics, a little bit of how it scales, because it's very computationally complex.
Right.
Well, it's very computationally expensive. So I
Right.
would have liked to see what your implementation was in a way, so I can more or less have an idea of how it will scale up, or if it's, for example, parallelized in a way. So if the
right. In principle, you could parallelize it. The problem is that, so if you are interested in this, is how can you generate, because essentially the most complex part of it is trying to calculate this k-bottom, the normalizing constant, which is just the summation of the power set of all the graphs of size n.
So everyone is different, let's say. So you can
Yeah. So for example, if you have the simplest case is if you have n equals 2, you have 4 cases, right? You have the empty graph, the fully connected graph, and then 1 to 0, and then 0 to 1, like as asymmetric connections. But the thing is that when this scales, how can you? The problem is, which I haven't found any solution yet. Maybe you know about literature on this. How can you generate the power set of networks of size 5 in a parallel fashion? Because right now, the only way that I can do is using a recursion in a serial way. And again, so when you have a network of size 6, which you can still use with this piece of software that I built, it's manageable. Even though it's like 1 billion terms, you can still do it. But when it becomes 7, now it's, I don't know if you can do it. But the thing is that that's my main issue right now, how to parallelize this, because it's not straightforward.
So but you've tried this with how many terms in a way? So have you tested the library on like several different graphs or whatever?
Yeah, kind of. So again, the simulation exercise was doing exactly that. So I was running this on 2,000 ergons. Estimate this model on over 2,000 different groups of pooled ergons. And each one of those different, right? So, yeah.
Any other question? Okay, no? Well, in that case, we can close the session. And, well, we have some time. So we will have to meet here at 6:50, right? So you can go outside and stretch your legs and maybe drink some coffee if there's still some coffee. Okay, let's meet again
so
here.
There's the public lecture after this. So I encourage you to come in. Janos is going to start.
Yes.
It's going to be awesome. So I think,
okay, thank you, George.
Thank you.
Hey!
I have to introduce now another very good friend, someone I admire very much. She's you will see her talk in a day or two, and she's at ISI Foundation as well. She works on epidemiology and has done incredible work. So I'm also very happy that she's here. Daniela Paolotti, please, and she's going to be the one introducing Janos.
Thank you, Leo, for the nice introduction. Thank you for being here till the very last moment. It is my great pleasure to introduce Professor Janos Kertes, with whom we have shared many collaborations in European projects in the past years. So it's a really great pleasure to see him here. Professor Kertes is the head of the Department of Network and Data Science of the Central European University in Budapest, Hungary. His work spans several areas of statistical physics and its applications, ranging from percolation theory, phase transitions, fractal growth, to granular materials and simulation methods. More recently, he has focused on several multidisciplinary topics, mainly focusing on complex networks, financial analysis and modeling, and as we see today, complex networks of human interaction. His work has been awarded with several international recognitions, including the Hungarian Academy Award and the title of Finland Distinguished Professor. And he's a member of the Hungarian Academy of Science since 2001. So please welcome Professor Kertes.
Thank you, Daniel. Can you hear me? Good. Thank you, and I would like to thank the organizers for giving me this opportunity to come here. This is my first visit to South America. And I apologize for my voice. I have brought this cold with me from overseas. So today I would like to talk about analyzing and modeling the complex network of human interactions. And I would like to start with a reference to authority, to Hawking, who passed away recently, who said that our century, the 21st century, will be the century of complexity. And in order to appreciate this, let us discuss a little bit what complexity is. I don't want to define complexity. It is easier to say a few words about what is not complexity. This is a watch. The watch inside of a watch, which is complicated. It consists of many little elements, but it has a linear chain of logic. If you want to understand what a single piece there makes, what is the role of it, you may wonder at first, but if you have long enough time and a good book, then sooner or later you will understand. Because of this linear chain of logic. And on the other hand, this is the human brain, and here we can say that this is complex because it is not enough to understand well what a single cell does, even if we understood completely what we don't. How a cell operates, we wouldn't understand how thoughts and emotions come about when these cells are connected to each other. So complex systems have, have a lot of important features. Some of them are listed here. There are many interacting components. There are feedback mechanisms. Non-linearity is characteristic for these systems, cooperativity, and emergent phenomena for which these emotions and thoughts are just an example. And there are many, many such systems. There is this bon mot which summarizes shortly what a complex system is. The whole is more than the mere sum of the parts. And there are many such examples, like the brain, as I mentioned. The cell itself is a complex system, the internet, ecosystems, and so on. And last but not least, the human society itself is a paradigmatic example of a complex system. Well, in the last 20 years or so, we have understood that there is a very important general feature characterizing these complex systems, namely that there is always an underlying network behind. There is a scaffold of a complex system, the network, and without mapping out this network, without understanding this network, it is hopeless to understand the complex system itself. So, in this light, we have important aspects of how to study complex systems. We have to identify this skeleton, this scaffold, the network, and then learn about the topology of this network at different levels, at the micro, at the meso, and the macro scale. Then uncover the relation between properties of the elements and the topology. For example, the strength of the ties or the weights on the links. And then we have to relate the network to the function of the system. We have to describe dynamic processes. After all, we have to understand the complex system itself, which operates like a dynamic system. So we have to understand dynamic processes on the network, and what are the influencing factors, including the network structure. And last but not least, we have to build models for understanding and for prediction. Modeling is at the core of my talk, but modeling means very different things depending on which discipline you are in. For a statistician, a well-fitting function is a model. And in this sense, there are very efficient models of the network of the human society, where somehow the network is described with many, many parameters, and this can be used for prediction in a very efficient way. It is enough for me to refer to the fantastic success of network science in epidemiology. But for physicists, modeling means something different. For physicists, modeling means that we want to understand the mechanisms. We want to have a causal construction which leads to the system. I usually refer to the Ptolemaic or Keplerian description of the celestial bodies, of the motion of the celestial bodies. Both are models in the first sense. The Keplerian is somewhat simpler, and therefore we would prefer it anyway. But the real model, which gives this feeling of the understanding, is that of Newton. So if I want to put it into a very ambitious way, and we are very far from that level, our goal could be to give a Newtonian model of the society. Well, of course, social sciences have always been dealing with the network of social interactions. And I would like to refer here only to two very famous observations or hypotheses. The first one is due to Mark Granovetter, and this is the title of his famous paper, The Strength of Weak Ties. The reference is always at the bottom of the slide. And this is the most cited paper in network science, whatever. It has got, according to Google Science, more than 50,000 references. And it says the following: it is a hypothesis about the small-scale behavior of the human social network. And I like to quote from the paper what it says. The first point is the definition of the strength of a tie. The strength of a tie is a probably linear combination of the amount of time, the emotional intensity, the intimacy, mutual confiding, and the reciprocal services which characterize the tie. And I like this definition because I always wonder what a linear combination of emotional intensity, intimacy, and the mutual confiding could be. This is for physicists somewhat shaky. Nevertheless, we understand what is meant by the strength of a tie. And the second point is the hypothesis based on this definition of the strength. The stronger the tie between A and B, the larger the proportion of individuals S to whom both are tied. This is also formulated in a somewhat complicated way. The meaning is very simple. The meaning is that if two individuals are closely related, then they share a lot of friends. That is it. And the interesting part of it is that although the hypothesis is about the local property of the network, it has global consequences. The global consequence, or the macro scale consequence, is that the society consists of strongly wired communities which are linked by weak ties. And that is where the title of the paper comes from, the strength of the weak ties, because these weak ties hold the society together. The other effect I would like to refer to is due to Robin Dunbar. It is from 1992. And it says it is about the egocentric network, so the network around an individuum. And it says that there is a limit to the number of people with whom one can maintain stable social relationships due to the finiteness of resources like brain capacity. Actually, that was what Dunbar was focusing on. But there are other limitations due to time or energy. And Dunbar also gave an estimate for this limit. He said that on the average, this is around 150, and that is the number of individuals one can have a social tie to. Where a social tie means that, according to Dunbar, I hear that from him himself, that if you meet this person at the airport, you immediately can start a talk with him or her because you know more or less about your circumstances and so on. So this is also a statement with severe consequences. First of all, it tells that friendship networks cannot be scale-free. Scale-free networks are very important, and they are ubiquitous, but a friendship network is not a scale-free network because there is a characteristic scale, namely the Dunbar number. And it has also dynamic consequences, namely, since this number is there due to the limitations of the resources, you can get a new member involved only if you get rid of another one which used to be there, or the other way around. If somebody leaves, then you can have a new friend. This picture shows you the refined Dunbar theory, which gives a structure behind this Dunbar number. There are circles. There is an innermost circle with the highest intensity and so on, up to 150, where the limit of the social interactions is. So these are, I think, the most important observations or hypotheses from social sciences. And since we are in the era of big data, the question is whether one can find evidences in favor of those observations or hypotheses. And in fact, one can. The first one I would like to show you is support of the Granovetter hypothesis based on call detail records. These are mobile phone records containing the time, who called whom, and how long, and so on. And, and this data can be used to construct a proxy for the social interactions. Because nowadays, the mobile phones are very important for everyday communication. We use them almost like an organ. Everybody has his or her mobile phone there, and we feel if it is lost like getting ill and so on. So this can be assumed to be a proxy for the social network. And then what we have to do is to find out, after mapping out the network, to find out what is the strength of a tie. And there is a very natural way to choose that in this network, namely either the duration of the talks between two persons or the frequency of calls. Both work. And this is very much in the spirit of Granovetter, because it is the time spent together, and it also has some financial investment behind it. So it seems to be a good choice. It corresponds to the Granovetterian strength of ties. And then what we have to do is to define mathematically this overlap function, which is shown here. You can see this OIJ. And this is a quantity which has the value 0 when there are no common neighbors for two neighboring nodes, and this is 1 if all the neighbors are common, where Nij is just the number of common neighbors, and Ki and Kj are the degrees respectively. So we have now the weight, we have the overlap function. All what we have to do is to make a plot, as you can see here. And this plot tells us that the Granovetter hypothesis is correct because there is a monotonous relationship up to 95%. Here something happens, and we understand what happens, namely this extreme case is when people talk a lot, some 15 or 20 hours per day. And in this case, usually there is a pair which talks to each other that much. And therefore, this is not within the trend. But for 95%, this Granovetter hypothesis is proved. And one can see that this is, in fact, the consequence of the relationship between the weight of the links or the strength of the ties and the topology. Because if we shuffle these weights and do the same experiment, then we get this red line with no relationship. So in this sense, we can say that the big data contributed to the proof of the Granovetter hypothesis. And we can see also that, in fact, the global consequences are also there. You have the communities with the light color, which are connected with the dark color, and this plot on the right-hand side makes this observation more mathematical. This is a percolation test of the Granovetterian structure. What is done here is the following. We remove one by one the links from the network. In the case of the black curve, we do it such that we first remove the highest weight link and the second highest and so on. And in the case of the red curve, we remove the weakest link first and the second weakest and so on. And what you can see here is that this is the order parameter, or the relative weight of the largest component, that for the red curve there is a clear percolation transition here, while no such a thing can be observed for the black curve. And this is even more pronounced when we consider the second moment of the cluster size distribution, which has a sharp peak at the transition point. And in fact, that is the case for the red curve, and there is no such a peak for the black curve. And this can be understood easily. If we remove the weak links first, then we just cut the connecting weak links between the communities, and therefore we generate a fragmentation transition. While if we cut into the communities, we cut the strong links, then we push the transition point much above. And therefore, the transition point in the black curve and in the red curve, the transition points are different. And the difference is delta FC. This is the black transition minus the red transition point. And if this delta FC is positive, strictly positive, then we can say that we have a Granovetterian structure. I'm going to use this delta FC later. So this is a study about the Dunbar number, how it can be approached from the point of view of big data. And this is due to Bruno, who is one of the organizers here, and his collaborators. And this study is the following. They took 1.7 million Twitter users over 6 months and calculated the out degree of the users and the weight in the sense of the number of replies from I to J. This is, of course, a directed network. And then this divided by the out degree gives the average out weight. And this represents the effort of user I, which can be distributed among the neighbors. And what you can see here on this plot is that this average out weight, this average effort on the neighbors is monotonously increasing with the number of neighbors at the beginning, but then the capacity is finite. It cannot grow forever. It has a maximum, and above that it starts decaying. And this maximum is around the Dunbar number. Oops, sorry. So these features I just referred to are just some stylized facts, but there is a lot of such observations or expectations. The Granovetterian structure, meaning that the overlap is a monotonic function of the strength of the tie. And the consequence is that this delta FC is strictly positive. We expect that there is a peaked degree distribution with a characteristic cutoff, which is the Dunbar number. Why do we expect a peaked degree distribution? Well, we cannot expect that the maximum probability for the degree is 1, because even autistic persons have more than one relationship. So we expect that there is a peaked distribution. High clustering is expected. Inhomogeneous community size distribution. There is a multiplex structure of the social network. I'm coming to that later in more detail. And we have also some theories about tie formation. Tie formation can be a consequence of focal closure or cyclic closure. The focal closure is when a person makes a friendship tie with somebody who is not related by any friends or chain of friends, but of course the relationship comes from homophily, or the cyclic, in most cases this is a triadic closure. This is something which you have already heard about in the talk by the previous session. So this is just the closure when there are, I have already two friends, and these friends get friends. One often says that friends of friends get easily friends. We have also some picture about how relationships are broken or vanish. There are different mechanisms for that. First is node deletion. If somebody dies, for example, or moves away, then the relationships are broken. One has to invest into a relationship, otherwise it fades away. Or, sadly enough, sometimes relationships are broken up. So these are all either based on theories of social sciences or simply by on everyday experience. So let me come to modeling. And let us first try to model a simple Granovetterian structure. We take n agents and we form links between them. How? Let us assume that there are already links, and then we have a mechanism which corresponds to the triadic closure. If node I is chosen at random, for example, then it makes a search among its neighbors weighted by the link weights. The higher the weights, the larger the probability that that neighbor will be chosen. And then this neighbor is chosen. That means that there is an effort made, there is a strengthening of that particular link or reinforcement, and with some probability, a triangle is closed. This is the triadic closure element. Then there is a link formation corresponding to the focal closure, and in this case, it is taken totally randomly. This is, of course, an approximation. No homophily is taken into account here. Later, I'm going to refer to the case where homophily is taken, is considered. So in this case, a node is randomly linked to another node, and an initial value of the link weight is given. And finally, there is a node deletion term where at random, with some probability, nodes are deleted. This is necessary in order to drive the system into stationary state. So this model has quite some parameters. P delta is the triad formation parameter. PR is the parameter which is the formation of the random link, and PD is the node deletion parameter, and the delta is the reinforcement parameter. It turns out that these three P's, these are necessary to influence such characteristics of the network like degree, size of the communities, and so on. What really matters here is the reinforcement parameter. And this is demonstrated in the next figure. So this is the picture we get if there is no reinforcement. There are no communities whatsoever. Here you can already see the emergence of some communities, and as the reinforcement parameter increases, you get more and more pronounced communities. And indeed, within the communities, due to this reinforcement, within these communities, the links are very strong. And these communities are linked to each other by weak links. And indeed, the global consequences are also there, naturally. This delta FC, you remember this was the characteristic difference between the percolation thresholds depending on which sequence we took in the removal of the links. This delta FC is positive, and the higher delta is, the larger is this delta FC. This is the model we call weighted social network model. And in this model, we can study the effect of the removal of the links. We can introduce the node deletion. This is how it was originally done. Then we can use link deletion corresponding to the breaking up of a relationship, and aging corresponding to fading away of a relationship. And in all cases, we see that the Granovetterian structure is robust. However, the structure is not the same. For the aging mechanism, community structures are clearly visible, and the link weights in each community are more homogeneous. So you get more homogeneous communities in this case. And of course, in reality, all three mechanisms coexist. So let us make a step forward and introduce some missing features. The weighted social network model produces non-overlapping communities. Communities are isolated and not, of course, connected by weak links, but they don't overlap. In reality, every one of us belongs to several communities. We have a family, we are members of scientific communities, we have friends, and so on. Namely, the society is a multiplex. Everybody participates in different layers of this multiplex, and that is the reason why we have these overlaps. So in this figure, which was taken from the paper by Anne and collaborators, one layer represents one type of interactions. Let's say these are the friends, and this is the family layer, and so on. And then one individuum corresponds to several communities, and therefore the communities overlap. And the question is, can we construct a Granovetterian structure such that it is a multiplex? And a naive idea to take two weighted social networks randomly doesn't work, because that totally destroys the Granovetterian structure. So instead, we have to introduce some correlation between the layers. The layers are not independent. And what we have chosen in this case was that we introduced spatial correlation. We put the nodes into a plane, and the probability in the focal closure, when we choose a random node to connect with, in this step, the probability depends on the distance. And this alpha parameter over there governs the strength of this correlation. If alpha is 0, then there is no correlation. If alpha is large, then the correlation is very strong. And here are the results. So this is alpha equals 0. It shows no Granovetterian structure whatsoever. But as alpha increases, we get something which reminds us to a Granovetterian structure. But we can make this, of course, more quantitative. In this diagram, we can see how this delta FC changes with alpha. It decreases somewhat as alpha increases, but it remains definitely a positive number. While the number of this delta FC starts from 0. Sorry, this is delta FC starts from 0, and it increases as alpha increases. And this is the number of communities a node belongs to. And that is large at the beginning, and it decreases, but it remains non-trivial also for large alpha. And that means that if alpha is large, we have both overlaps and Granovetterian structure. Well, the next step would be not to make the focal step totally random, but to take into account homophily. We know that homophily is a main governing principle in type formation, and that can be done in the following way. We have to assign attributes to the nodes, traits. In fact, there are F traits for each node. That's a simplification, that this number is the same for everybody. But this is acceptable. And then we have for each trait Q different possible values. If somebody knows the Axelrod model or the work by Maxi San Miguel's group on it, then this approach will be familiar. So in this case, every individual can be characterized by an F-dimensional vector. And the values correspond to the values of the individual traits. And now, when this focal closure step is done, then first one of the traits is chosen at random. And then there is another individuum chosen, but only from those set where the value of this particular trait is the same. So in this way, this homophilic attraction is at work. And similarly, one can also take into account this feature in the triadic closure, where again trait is chosen, and only for those partners where this particular value is the same, the game is played. The following interesting observation can be made. As a function of the number of traits, F, we see a non-monotonic behavior. For example, here in the average degree, there is a minimum. The different colors correspond to different Q values. For the clustering coefficient, we see, I'm sorry, we see a maximum. And it is it is good to define the so-called feature overlap, which is the average overlap where sigma IF is the trait value of node I, node I's fth trait. If this feature overlap is 1, that means all the traits are the same. Then we call this pair matching. And here you can see that the feature overlap is 1 for quite a number of, quite large value of f, depending on q, of course. And also, we can measure the number of communities per node. And the number of communities per node is 1 in the same interval where this feature overlap is 1. So how can one understand that? Well, it seems that there is a critical value of the number of features. And this below this critical value, we have a segregated phase where the communities are all homogeneous. And above this critical value, we have heterogeneous overlapping phase. Moreover, we can do the following reasoning. If we choose, as we do, always uniformly randomly from the q possible values, then the number of nodes sharing a specific set of traits is on the average n over q to the f. And the transition occurs when this number becomes less than the typical degree of the original weighted social network. This gives us a characteristic degree. Of course, this is a hand-waving argument, but it suggests that this value this variable n over q to the f is a scaling variable. And indeed, that is what we see. This is the average degree as a function of n over q to the f, and it beautifully scales for large n. And this dashed line marks the critical value of f corresponding to the argument I presented. And here are the communities depending on whether we are, on which side of the critical f we are. A and B are for values where we are below the critical f. And you can see that either we have a totally homogeneous community, this is all the nodes are matching, or we have one single node which is connecting two communities, but the rest is very, very homogeneous. While here we are above the critical value, and you can see that this is an inhomogeneous community. And finally, C corresponds to the critical value. And you may ask, why is this interesting? Why is, this number of f is given for a person, usually very high, because we cannot be characterized by only a few traits. Why is this interesting? Well, there are situations when, in spite of the fact that people have many, many traits which they could compare, they reduce themselves to a few. And only a few matter. For example, religion matters, or race matters. And in this case, you get, irrespective of all the other traits, which may or might connect to people, they don't matter, and you get the segregation as shown above. Okay, so by these examples, I wanted to show you that incorporating more and more known aspects of social networks, one can do better and better models of the society. Of course, we always want to compare to the data. After all, the empirical data should tell us whether we are on a good track or not. And usually we use communication data. Basically, all interactions in the society can be considered as communications. And nowadays, most of them leave digital footprints. So we use this digital data of communication and use then the data observed from the communications as a proxy for the social interactions, as I already emphasized for the mobile phone network. So let us see what does that mean for a very simple question, namely the degree distribution. Okay? So let us see communication networks, degree distribution. Twitter, this is Facebook. These are different communication networks, mobile call network. What is the common feature of all these observations? All the degree distributions you can see here are monotonic. These are from the observations. But I would like to remind you to the stylized facts, peaked degree distribution with a characteristic cutoff. So already at this very simple test about the degree distribution, you cannot have a simpler characteristics of a network. We see that the observation from big data on communications contradict to a stylized fact. What is behind that? Well, we have already discussed that the society is a multiplex because of the different kinds of links. But the society is a multiplex also from the point of view of communication channels. So this is an individuum, this black line, and these are the communication networks depending on which channel this individuum uses. Face-to-face, email, mobile phones, Facebook, or aggregate networks. And the aggregate is when we take everything into account. And when we analyze one set of data, for example, the mobile phones, then we don't use the entire information because we don't have access to it. We use only one layer information. And if we use one layer information, that introduces, of course, a bias. And we would like to understand why is it so that whichever layer you take, it introduces such a bias that the maximum of the degree distribution becomes 1. That's strange. Well, before going into that, let us have a closer look at this degree distribution by trying to sort out the mixture users. I mean, people use the different channels with a different frequency. They are attracted to the different channels differently. So if somebody uses very heavily a channel, then we can say that this user is a mature user. And well, as you can see, if we restrict ourselves to the mature users, then a peak emerges. So that already tells us something about the origin of this artifact. So in order to understand how this artifact comes from, or where this artifact comes from, we make a model of channel selection. We define a degree of preference of a person for a particular channel, channel C, and call it as an affinity, FIC. And people who invested more into a particular communication channel prefer, of course, to choose it. And that is why they invested so much. And they have, therefore, higher affinity. And now the situation is the following. I want to communicate with J. And of course, I want to avoid the channel with low affinity for J. So therefore, these persons, I and J, if they want to communicate with each other, they choose a channel C with a probability which depends on their affinities. And the simple choice for this probability is that we just take the minimum of these two probabilities. And this minimum choice favors the channel with high affinity for both, of course. And then we can start from a network with a peaked degree distribution. This can be a regular network, regular random network, or a Erdős-Rényi, or we can take it from our weighted social network model. And then, according to this selection rule, we consider a link in the layer established with this probability. And one can solve this analytically. I don't want to go into it. But this is the result. The result is that although we started from peak distribution, in fact, the random regular is extremely peaked. It is a delta. You get a monotonic degree distribution. And this is, of course, also the case for the weighted social network. Also, we can show that the effect for mature nodes can also be reproduced. And we don't have to restrict ourselves to this very simple model. So we have a feeling about why this artifact comes about. But it is interesting to see whether there are other effects strengthened by the choice of the channel. This is a plot of the neighbor's average degree, and if it is monotonously increasing, then we say that this is a degree assortative network. And all the communication networks are known to be assortative. But again, we can show that if we start from a non-assortative network, and use the channel selection as I showed, we get an assortative network. Which doesn't mean that the networks are not assortative, it just calls the attention to this effect that it may have a strengthening or may lead to some artifacts. Okay, so we have a collection of stylized facts about the complex network of social interactions. based on social science studies, big data investigations, and common sense. Data-based evidence in favor of social theories, Granovetter, Dunbar, and so on, is accumulating. Models with simple link formation, deletion mechanisms, focal and cyclic closure, node deletion, link deletion, and link fading or aging, give reasonable results on network structures, and incorporation of homophily, multiplexity is possible. Big data should be handled with care, as bias due to channel selection may lead to artifacts. But of course, this list of stylized facts is far from complete. We haven't spoken about kinship versus friendship, although we have heard a very nice talk about that. Sex. This is a very boring society. There is no sex here. This figure shows that the best friend, meaning that the most actively communicating partner in a society, is usually of the opposite sex, but the second best is homophilic. We haven't spoken about negative links. Not everybody is an angel. There are dynamic aspects, circadian and other regular patterns. Mobility, these are interesting motifs of mobility patterns. Burstiness, these are all influencing very much the dynamic behavior of the social network. And there are many more. So this is a very rich field, and I invite you to join and work on it. And finally, I would like to thank my collaborators. There are so many that I don't read all of them. From Finland, Korea, Japan, Mexico, and Hungary. And these are the funding agencies. And let me call your attention to these advertisements. We are taking PhD students, and we are hiring faculties. Thank you for your attention.
Thank you so much for a great talk. So I invite the audience to ask questions to our speaker. I know it's very late, but I think there's time for a couple of questions. Let me get the microphone. Okay. Do you have questions?
Thank you, Janos. That was a fantastic talk. So in a way, alpha was the core or the heart of your multiplex argument and the argument later. You seem to assume, this assumption seems to be that alpha is a parameter.
Yes.
But why? I mean, it could vary, even if it was a parameter, it could vary among the layers, but it could vary even within only two layers within the network. But it could also be a variable.
This is true. Actually, the situation is even more complicated because, of course, there are other types of correlations, not only geographic correlations. We wanted to have a simple model. And in a simple model, you have one kind of correlations, and you parameterize it with one parameter. And that was enough to show the effect. Of course, this is not enough to match model data with observations. And you are right, and in such a case, one should take care of other types of correlations and not uniform and so on. So that would be a refinement of the model at a level which we wanted to avoid at this point. But this is very valid.
I have a follow-up. Do you think it's possible that some of the mechanisms in different layers actually evolve to manipulate alpha, to manipulate the probability of the distances among the You could think that maybe Facebook is
I think this is more complicated. So if I understand correctly what you are suggesting, is that one could make this somehow self-consistent. That you somehow have a feedback mechanism and then let the system converge to a state where everything fits together. And I think that this is more complicated because there are possibly such feedback mechanisms, but on the top of that there are exogenous effects and all kinds of other couplings which would make this a closed system. Thank you. Oh, thank you very much. Thank you. Thank you very much indeed.
Yes, have a good night. It's been a very long day. Thank you, Janos. That was awesome. So, no. So, thank you very much for staying this late. I mean, I think you've been rewarded. We all love hearing about science. So, tomorrow there will be a little bit shorter schedule, so we will not be dead by the end of the day. Please, thank you very much for coming and staying this long. I'll see you tomorrow. Thanks.
Okay, good. Thank you. It's really a little late, I'm afraid.
Yes, I know.